compared to recent approaches that are shown on this table on the right. So in order to do this, we developed a deep learning architecture composed of a deep convolutional neural net and long-term, short-term memory net. We trained our classifier on generalized features extracted from VR headset sensor data using head tracking, hand tracking, and eye tracking in order to detect distraction in our educational VR environment. So consumer level VR displays such as the MetaQuest Pro now come with varied sensing such as eye, head, hand, and facial tracking. However, less work has been done on classifying distraction with such sensor data in educational VR. So raw sensor data like this can be fairly complex to classify, so researchers have turned to using machine learning approaches. As you can see here in the table, some works have found success in nonlinear kernel support vector machines. Deep learning shows more promise, and a recent approach on the bottom using a CNN LSTM model achieved a higher accuracy. However, there were some limitations, including learning with absolute position data, learning with timestamps across multi-event sessions with fixed event timings, repeated data points to balance class distributions, and overall detection per session rather than narrow per event detection. Training on these kinds of information can cause classifiers to overfit by learning unrelated features such as headset fit position, participant heights, or timing of events or interactions, thereby reducing a model's generalizability. So in order to address this, we considered a deep learning approach using generalized features based on head, hand, and eye data collected from a study where participants immersed in VR using a Vive Pro Eye device and Vive controllers took a field trip to a virtual oil rig. Educational content was presented by a pre-recorded 3D RGBD-based teacher avatar that you see on the right. This was composed from pre-recorded color and depth videos that were captured by a ConnectV2 at 30 FPS, and we used a green screen to reduce edge artifacts. So after a tutorial, subjects visited 6 areas where they learned about devices used in drilling operations. Subjects held a virtual mobile device for general use, interactions, and distractions. So in the figure on the right, each area had the teacher point out and explain 3 devices. One of those 3 times, the virtual mobile device presented a distractor in the form of a text message with an accompanying vibration and sound effect. The message prompted the participant to click on an object. So in this video, you will see a participant get distracted by the distractor. So we randomized the order of distractor occurrence across pointing events in an area in order to reduce subject anticipation of distractions. If the subject ignored the distraction, then at the end of the area, the teacher avatar reminded them to address all outstanding prompts on their mobile device and paused until they did so. So we collected data from 37 participants as reported from the Vive Pro Eye device and recorded world space positions of the phone, head, and hand in the virtual environment. So first we filtered out invalid values and replaced them with linearly interpolated values based on last valid and next valid values. And we also applied a moving average filter to reduce noisy data by taking the average of 6 neighboring data points for each field. Angles were calculated from 2 direction vectors using the following formula. We computed the angle between the subject's eye gaze direction and the direction from the center of the subject's eye to the teacher, as well as to any pointed at objects, to the phone, and to any distractor task objects. We separated 3D eye gaze and head gaze directions into yaw and pitch. We applied the same approach to compute angles, but using the subject's head gaze direction. We then computed velocities for each angle and position as interframe differences per time step. Finally, left and right eye openness values were averaged to produce a combined eye openness value. Left and right pupil diameters were averaged and combined as well in the same way. So we have considered 2 classes representing our conditions for classification, distractor and no distractor. We took a 5-second window of data from the interval when the distractor was present while the teacher pointed. We also took a 5-second window of data from the interval where there was no distractor during teacher pointing and labeled that as having no distractor. Finally, this made our data set consist of 444 event windows for a total of 230,680 data points with an equal distribution per class naturally. We normalized feature values with min-max normalization and standardization. So for classifier training, we use standardization because that led to better results. So finally, to select features, we use the chi-square test. Important scores are shown in the graph on the right for the remaining features. This score describes a decrease in the mean accuracy in the random forest classifier when feature values are randomly perturbed. So we split our data set using an 80-20 split into training and test sets, randomly choosing from 444 event windows. We considered the following 1D deep learning approaches for classifying our data. CNNs extract features from and classify on a sequence of observations. This generally tends to fit well for time series data like ours. CNN LSTM add a long short-term memory network which retains input based on change in values considering prior time steps. This allows back propagation to be considerate of time. The design of our deep CNN LSTM network is inspired from the VGG16 architecture where they stack convolutional layers allowing for deeper feature extraction. However, different from that, we just remove the fifth convolutional layer and add in an LSTM network. And finally, we used Keras to implement the models and train them. For all of these models, we used a batch size of 512. So we evaluated the performance of the classifiers using the F1 score, precision, and recall for each class. Our results showed that our deep CNN LSTM classifier improved accuracy for classifying distraction. This implies that improving generality of features and depth of convolutional neural networks can actually help with creating a more accurate and robust classifier that detects distraction in educational VR. So some of the limitations of our work included labeling the data based on the condition provided. This actually does not guarantee that all people were distracted or not distracted in those conditions. Further consideration of this during labeling could increase classifier accuracy. We did not validate our model's generalizability on data from an unrelated task or from an offline environment. And finally, we only used a small subset of our data for training and testing. So this limited us to supervised deep learning methods, which add a little bit of tedium by requiring the data to be labeled. Unsupervised methods such as k-means tend to perform poorly as distraction classifiers and were not really suitable with our data set. Therefore, we suggest the following improvements. Our deep learning approach could be extended with additional physiological sensing, such as electrodermal activity, electroencephalography, or electrocardiogram. Given that a deeper CNN network improved accuracy, future work can consider applying recent deep learning advances in anomaly detection using larger data sets. These can include encoder-decoder-based generative approaches that compress features into latent codes and can decode those into useful learnable representations. This can help reduce feature complexity for the distraction classifier. These can be transform-based methods with attention mechanisms or even variational autoencoders. And finally, privacy-related aspects could be considered by integrating modularity. This is by using only signals that a user opts to share. This would work with gatekeeping modules that prevent detection of user properties by limiting features to only those needed for an activity. So any questions or answers? I mean, questions, I'll answer. Otherwise, that's it.
Okay, so I have a couple of questions. At first, I would like to see your video of the experiment again, because video time was very short.
All right, the video of my experiment. So. All right, so that is a teacher pointing with the distraction. Now here you will see a teacher So that showed a teacher pointing, but there was no distraction that happened.
The distractor conditions, user was forced to click the smartphone, a kind of smartphone, right?
So they did not have to click it until the very end. If they had not, done the task, this distractor task, the teacher just reminded them to do it. So a participant could actually decide to ignore it and wait until the very end to address it. Yeah, so they were forced to do it, but they had the option of delaying it.
So if they should click or not for each distractors.
Yeah, so they could choose not to click on a distractor.
Which situation you'd like to detect? So the existence of distractor or the situation when the user participant was really distracted? I mean, so I'm wondering what will happen even if the notification of the smartphone is displayed to the user, but so user ignores this notification. So what will happen? So I mean, just user was looking at smartphone briefly within a very short period, but user did not click interact smartphones. Would you like to detect this kind of situation?
So yes, that is actually a limitation of our work. We can't detect that, but one of the improvements is that we would like to add in like some additional sensing that might help with being able to detect something like that. So our motion features are pretty much just detecting their motion. So if they look very briefly at it, it is more likely to think that, okay, they actually, they got distracted or something. So it was actually detecting that, which may not. So what we would really like is to be actually able to detect, the distraction of a user as opposed to the presence of a distractor from user data. So that is definitely an extension we are considering in future work.
Very interested in this research because I'm also working on a very, very similar topic in the presentation trainings. So yeah, but so okay, is there any question or comment from the audience?
Very short question. Could you tell me the reason why did you employ the virtual oil rig environment and point and click scenario? Is there any specific purpose to teach something relating to oil rig, or is it just you could use that virtual environment?
Part of it was so we could use it, but also virtual or oil rigs have been used in training before for teaching people about how devices that are used on drilling operations. So these are very big devices that can, when you point them out, it's very obvious to see what they are. So that was the benefit, is that it had very large objects, and it was a very large kind of thing with a lot of devices that we could talk about. So this allowed us to have more areas and more things to talk about, which gave us more opportunities or more like, trials where we could present a distractor. So it was kind of like, yeah, we did it because we wanted to, but also it fit in with what we wanted to do.
With a great inspiration, because we often use a very too much simple scenario about our environment to test similar things, but this kind of complicated structure is so much useful for me to see. Thank you.
Yeah.
Is there any question or comment?
Hello, thank you for the presentation. I'd just like to know if this method requires you to have certain objects to be labeled as something that you should be looking at if you are not distracted. So if this method can be extended to more general situations where users do not have a specific target that you should be looking at a certain time.
So that's you're actually right about that. So in this case, we did have, the teacher is a labeled object, something that they could be looking at, or like, the object that the teacher is pointing at is also another labeled object, but we did not assess, we also labeled the distractor task object as well, something that they shouldn't be looking at. But that is a limitation, is that actually, we focused it on labeling like things that they should have looked at versus things that they shouldn't have. So one of the things we actually considered, but we didn't do in this work, is kind of like an attention score mechanism that, based on where a teacher is looking or the student is looking, it would compute a distraction score, and then that score would be something much more generalized, so that you can then extend that with something like our approach. And then that would actually make it more generalizable as opposed to relying on labeled objects. We did some recent work, but it is still in progress, but some recent work is like the notion of like a generalizable 3D hotspot. So this would output like a distraction scores that could be combined, and then the sensing part of it would be our approach, and that would be detecting, distraction or no distraction, and that's one approach to it. Might be going on a bit too long rambling about this, but yeah, you're right. And we are considering on how to address that in a future work.
Thank you very much. So we run out of time. So let's thank the speaker again.
Thank you.
Have additional questions, please post your question on the Discord channel. Okay, so move on to the second presentation. The second presentation is gaze guidance in the real world by changing color saturation of object. The authors are Junpei Miyamoto, Hideki Koike, and Toshiyuki Amano. The presenter is Koike Sensei. Okay, so please start.
Okay. Good morning, everyone. My name is Hideki Koike from Tokyo Institute of Technology. So today I'd like to talk about the gaze guidance in the real world. And most of the work was done by my students, former student, Junpei Miyamoto, but he cannot come here because of his job. So, and also this is a joint work with Professor Toshiyuki Amano of Wakayama University. So here is a background of this research. So there are great demands on gaze guidance, gaze navigation in several domains, such as digital signage or electronic market, or et cetera, et cetera. But however, people often feel annoyed by overt, some aggressive visual stimuli, such as color changes or flashing lights or something else. So here's a related work on the gaze guidance. So this is mainly done on the computer displays. So let me talk about some gaze navigation on the computer displays. So here is the image. And this is another image. Did you realize the difference? Again, here is the first. This is the second. Did you realize? Maybe not. So here is a part. So the resolution of this part is slightly changed. Did you understand? Okay. So this is a heat map of the gaze positions. So if we change slightly the resolution of the images, the people's gaze is guided to that area, even if you did not realize these changes. So this is a gaze guidance. So our main goal of this work is, can we do this gaze navigation in the real world, not on the computer display? So this is our objective of our motivation of this research. So to do this, we used the programs, the project camera systems to project the images onto the real object and change the appearance of the objects. And we proposed some image filters. One is a shift filter and one is saturation filter. Let me describe this one by one. So this is the overview of our approach. So here is the objects in the real world. And the camera inside this program will capture these images. This is a captured image. And we changed this captured image by using image filters in here. And the target object will not change. So this is the image to be projected onto the real object. So we project this filtered images onto the real object by using this projector. So this is our program systems. And one of the important feature of this program is this is a coaxial program system. So we could do a dot by dot projections. So if we capture the images and then we can project the dot directly onto the exactly the same position of the real object. And we do not need many times multiple calibrations. If we calibrate the program systems one time, so we cannot do the recalibration processes. We do not need to do the recalibration process. So this is the image filters. So here, this is a shift filter, and the right one is a saturation filter. If you see here, the object, this creamy tomato noodle, is not shifted, but other objects are shifted slightly. Did you see the difference? This is very hard, but anyway. So this is saturation filters. This curry noodle is not is changed slightly. This its saturations, and other saturations is slightly decreased. So this is a shift filters. So we slightly change the dot by using some algorithms. This is not so hard. And also this was proposed by Miyamoto in 2018. So this is the original captured image. And we apply the shift filter and project it back onto the real object. So here is videos. So this is objects. And if we apply the shift filter, you will see that this object is not changed, but other objects were slightly shifted. So even if you put any other real objects, you could see the same effects. This is very hard to describe in the presentations, but you might not believe me, but if you come to our lab, you will believe. Anyway, so this is another saturation filter. So saturation filter changes the saturation of the object by using this formula. Please refer to our papers. This is not so hard. And if we change the parameter S, we could increase and decrease the saturation value of the objects like this. So this is the example of appearance change by using saturation filters. So this is a captured image. And this is the saturation, the image after the saturation filter. And this is a projected image onto the real object. So you will see a curry noodle is slightly brighter. But again, you will not realize this slight change of the saturation change of the object if you see this. And this is a paperback pattern. And this is the original image. And this is a saturation filter. And this is after the projections. So this paper, this book was slightly changed its saturations. So we did some experiments to prove our shift filter and saturation filter is effective. So we used this noodle cups and paperbacks and also stuffed animals. And the subjects was sitting on this chair and see those real objects. And we project the image onto the object. So once he answered, he see some object of the, he see the real objects. Then he asked to close his eyes, and then we will rotate the object to another pattern. Then we use a gaze tracker to measure his gaze positions. And this is the heat map of the fixations. The yellow box shows a target object. It means the object that which is a saturation or a resolution. Resolution, sorry, whose saturation has changed slightly. And this is a heat map of the fixation point. So this is a succeeded case, and this is also success. This is success. This is success, but this is failure case. So this here is a target object, but the user's gaze is guided to here. So this is success. This is success, and here is another failure, and here is another failure. But most of the cases we succeeded to navigate the people's gaze positions. So here is an experimental results. So by our experiments, the significant difference was identified in noodle cups and the paperback books as shown in this table. But a significant difference was not identified in stuffed toys. So that is because this was very depending on the material of the real world objects. So if the object is very, how can I say, it has a very reflected materials that we see some reflected light from the object because we use projectors. So in that case, it is very difficult to navigate the user's gaze positions naturally. But in case of noodle cups and paperbacks, it was almost succeeded. And here is another experiment. So we changed our experimental conditions and we used the stuffed toys. And 40 subjects was asked which object you saw after you opened your eyes by using this the projector camera systems. And this is an original image. So original image means the same image is projected back onto the real object. So we didn't do any saturations. But in this case, we did some saturation changes. So in this case, there are no difference between each object. But in this, after the saturation filter is applied, the people's gaze is guided to this object. So in summary, we propose a real-world gaze guidance method using a saturation filter. And the saturation filter is effective in guiding the user's gaze. And the saturation filter is effective for objects with a chromatic color. While a shift filter is more effective for objects with text, such as noodle cups. And we use a coaxial program systems, and a coaxial program is very useful because it enables a dot-by-dot projection onto the real object without recalibration. Okay, thank you very much.
Thank you very much. Okay, so now move on to the Q&A session. So is there any question or comment from the audience?
Thank you very much. Have you thought, I'm sure you have, but have you thought about other filters that you could use, and specifically dynamic filters? So some shaking, brief shaking, or changing the saturation, because you're projecting live, so you can maybe change the saturation over some time?
Yep, we did consider such dynamic filters, but as I told you in the first slides, we want to navigate the user's gaze as natural as possible. And such dynamic effects, such as flashing lights or changing the object's movement. In that case, the people sometimes feel it's very annoyed. So that's why we're using a static filters in this case. But as you said, that such dynamic filter will be effective in another cases. So thank you very much.
So I agree. If you do it very subtly, though, maybe they won't notice actually the blinking, but maybe it will be subtle enough, and maybe a little bit stronger.
Maybe.
I don't know.
Maybe, but as you know, the human's peripheral vision is very sensitive to the moving object or such changes of the color or some patterns. So I don't know, but yeah, you might be right, but we didn't do such the dynamic filters, but it could be considered. It would be considered. Thank you.
Yes, also thank you for the talk. I was wondering, because I think if I understand correctly, it sounds like all of the filters are kind of prefixed in the parameters, like by how much you shift the saturation and the shift. Have you considered using something like an image error metric or a video error metric to find out what would be the perceptual threshold of seeing a difference in that part of your gaze, such that you can direct the parameter by how much you blur the rest or by how much you saturate? Have you considered that?
That is very good questions, but we didn't analyze, or we didn't consider such color parameters as right now. But we did some experiments, and in our experiments, we used the parameters which was mostly effective to the human's gaze guidance. So, but we didn't consider such color parameters. Anyway.
Okay, thank you very much.
Thank you.
Any question? So I'm curious about if the experimental participant is really did not notice this visual effect. Did you evaluate?
Yes and no. In the first experiments, we didn't talk about anything about the saturation or shift filters, so they didn't realize after experiments interview. So most of them said that they didn't realize the saturation changes. But in the second cases, we didn't.
That's very interesting. Okay, so we ran out of the time. So let's thank the speaker again. Thank you very much.
Thank you very much.
Okay, we will move on to the third presentation. Third presentation is manipulating the sense of embodiment in virtual reality, a study of the interactions between the sense of agency, self-location, and ownership. The authors are Martin Guy, Camille Junet, Guillaume Moreau, Jean-Marie Norman, the presenter is Martin, right?
Yeah.
Okay.
Thank you for the introduction. Hi, I'm Martin, a PhD student from Central Nantes in France, and I'm going to present to you the work I have done with my supervisors, Camille Jeunet-Callouet, Guillaume Moreau, and Jean-Marie Normand. This work is about manipulating the sense of embodiment in virtual reality and studying the interaction between its components. The sense of embodiment is a feeling to be in a body that feels like ours and respond accordingly to our actions. That is, in the context of VR, the feeling that we perceive an avatar like our own body. According to Kiltony and colleagues, the sense of embodiment is based on 3 elements: the sense of agency, the sense of self-location, and the sense of body ownership. Previous studies have shown that manipulating the sense of embodiment can be made by manipulating each of the components. However, the relationship and the interaction between these components remain unclear as of today, especially in a VR context. The sense of embodiment is studied in multiple communities, such as neuroscience, philosophy, or cognitive science. But in this work, we focus only on the VR community. We will review how each component of embodiment is manipulated in the literature in virtual reality. First, the sense of agency, the feeling that I am the one in control of my action. In VR experiment, it can be manipulated with a biased visual feedback. That is when the outcome of an action is not the same as intended action. For instance, I am moving my second finger up, but instead this is the 4th finger that is going up. Then the sense of self-location, the spatial experience to be in a body, can be manipulated in VR by changing the point of view of the user in the VR headset so that the user sees the avatar from afar. So either the user is in first-person perspective, or there is a third-person perspective where they see their avatar from behind. And finally, the sense of body ownership, the oneself attribution of a body. It can be manipulated in VR by changing the avatar appearance, for instance, replacing the hand by a wooden block or a cursor. We just reviewed how each component can be manipulated in a VR experiments. However, each manipulation can impact the other components as well. So, and this is an important aspect to understand if we want a better knowledge about embodiment. For instance, body ownership and self-location are strongly coupled. If we are in a third-person perspective, which will impact self-location, it can also lower the body ownership as well. The link between the sense of agency and body ownership tend to vary from studies to study. As we just saw, changing the appearance of the avatar will change body ownership, the feeling of body ownership. And in some studies, it will impact also the sense of agency, but in some other studies, there were no impact of the avatar appearance. The link between agency, the sense of agency, and sense of self-location has not been really studied yet in VR. And to the best of our knowledge, we are the first experiment studying the interaction between the 3 components at the same time in the same experiment. In this work, our aim is to better understand the sense of embodiment and the interaction between its components by experimentally manipulating independently each component, and also to study to what extent we can selectively alter each component. So to do so, we designed a within subject experiment where participants realize different hand movements, in which, in some conditions, the sense of embodiment was manipulated by manipulating either of the 3 components, and participants realized different hand movement to add more variety to the experiment. So in this experiment, we manipulate one or more components of the embodiment. So we will review next how we manipulate each of this components. We followed the literature as presented earlier. So for the manipulation of agency, we have 2 conditions. First, a synchronous condition where there is a direct mapping between the avatars, the participant's hand and the avatar's hand, what we can see on the video on the left. And we have a manipulated condition with a biased visual feedback. There are multiple visual bias that we introduced. Either some fingers are inverted or there is a temporal delay in the movement. We can see on the bottom right. And there is also a finger, the thumb moving by itself. We added multiple bias to add some variety in the experiment and to be more representative also of tracking issues that could happen in VR scenarios. But in the analysis, we do not differentiate between these different bias. So we only have two conditions, a synchronous condition and a manipulated condition. Regarding the sense of self-location, we change the point of view of the user by shifting it to the right. In the video, we can see a green hand that is the user's real hand. This is just for illustration purpose, but it is not since the participant couldn't see it. So we have three conditions for the self-location manipulation, either a first-person perspective condition and two third-person perspective condition. That is because Maiseli and Slater found that when we shift the user's point of view with some overlapping with the real participant's real body, the sense of body ownership is preserved. But if we shift it too far, the sense of body ownership will break. We wanted to replicate this result. That's why we have two third-person perspective conditions. One when we shift at 20 centimeters from the participant in the peripersonal space, and one at 50 centimeters out of arm reach in the extra-personal space. Finally, we have two conditions regarding the sense of body ownership by changing the avatar appearance. Either we have an anthropomorphic hand, a cartoonish hand, or the avatar has a kind of hand composed of sticks, the stick fingers condition, which notably has no wrist. Because according to the literature, we wanted it to be as less anthropomorphic as possible so that the body ownership is biased. But since we have had finger movements, we still needed to have some kind of fingers. That's why we have these sticks that act as fingers. So we have in total 12 different conditions, 2 times 2 times 3 for 3 factors. And participants had to perform right hand movement for each condition, 1 time for each movement type. We have 3 different movements. And because of this high number of repetitions, each repetition lasted only 6 seconds to keep the experiment as short as possible. At the end of each repetition, participants had to report on the 7-item ICAT scale their level of experience, agency, self-location, and body ownership. They filled the questionnaire directly in virtual reality with their left hand. And there was 1 question for each component adapted or taken from existing questionnaires. For each of the 12 conditions and each of the 3 components, our dependent variable is the average score over the 3 repetitions. Now that we have seen the experimental protocol, we can see the result of our experiment. We will review each score of each component separately, one for each of our dependent variable. So we have the agency score, the self-location score, and the body ownership score. And for each of our dependent variable, we perform the 3-way ANOVA. So in total, we have 3 3-way ANOVA. And in the following, we will present only the relevant results. Regarding the impact of the manipulation on the score of agency, we can observe an interaction between agency manipulation and self-location manipulation. And notably, we can observe that only when the agency is not manipulated in the synchronous condition, the score of agency is higher in the first-person perspective, in green, compared to the both third-person perspective condition. Likewise, we can observe an interaction between the agency manipulation and body ownership manipulation. And we can observe an interaction between agency manipulation and body ownership manipulation, and only in the synchronous condition we can observe that the body ownership manipulation have an impact on the agency score. Probably that is when the sense of agency is manipulated with a delay or inverted fingers, for instance. The score was already too low for manipulating the body ownership or self-location to have an impact on the sense of agency. Regarding the impact of the manipulation on the self-location score, we obtain the same kind of pattern. Only when we are in a first person perspective, sorry, there is an impact of the other manipulation. So manipulating the agency or manipulating the body ownership will impact the self-location, but only in first person perspective. Probably this is the same reason as before. The score of self-location was already too low to the other manipulations to have an effect, probably. And finally, for the score of body ownership, things get more complicated because we find a three-way interaction between all the manipulation. But we can observe notably that both third-person perspective condition negatively impact the score of body ownership. And we can also notice that the body ownership score is lower when the movement is manipulated than when it is in real synchronous. That reinforces the hypothesis that the agency and body ownership are dependent. So to summarize our work, we are the first experiment to study the three components of the embodiment at the same time. And we found a strong coupling between agency and body ownership as found in the literature. However, the reason and the real cause is hard to tell from this work, and further studies are necessary. We could not dissociate body ownership and self-location as is in the work of Massely and Slater, and we instead found a high correlation between these two components. And finally, this is a new result in the literature, and we find a dependence between agency and self-location. As I said, further studies are necessary to better understand these results. For instance, we could use a standardized questionnaire because right now, since we had a lot of conditions, we only had this short questionnaire of 3 items after each conditions. Maybe we can adapt the task to have a longer embodiment phase so that we can have a longer standardized questionnaire using the literature that could help also the comparability between experiments. Thank you for your attention, and I will be happy to answer your questions.
Thank you very much. So Q&A session, is there any question or comment? I'll check Discord. No. Okay, so I'm very interested in this research. So maybe, when I write my paper, next paper, I will refer this one. And so, I think the current result is very understandable. So you cannot find the independence of each factors. But so I think this result is, at least for me, this is very consistent with my intuition. So yeah. And so if you make the situation approach to the actual real world, first person perspective, and I don't know, real hand and synchronized movement, so you can get higher sense of agency and higher body ownership and higher sense of location, right?
Yes.
But so I'm curious about, it may not be related with your topic, but I'm curious about, the possibility of increasing these factors more than the actual real environment. So do you understand what I'm talking?
I'm sorry, I'm not sure to understand what you mean. If you want that we can manipulate even more the sense of embodiment or increase the level of embodiment?
Yeah. For example,
the base level of embodiment. And your question is how would we do?
So for example, by combining your findings,
Yeah.
so would it be possible to increase the sense of agency or sense of embodiment? More than the real world view.
Actually, with these results, that could more help to study better the sense of embodiment, because we could design better experiments, that more controlled experiments. But actually, we cannot right now with this result improve the sense of embodiment. We just, for instance, if we had found that we could selectively attend each experiment, we could design new experiments to have a better measurement of it, designing new questionnaires or other measurement methods that could then lead to a better measurement of embodiment and increase this feeling by default.
Okay, thank you very much. So we almost run out of time. One short, quick question.
Thank you. So I want to carry on what you just said. I think that if your subjects are maybe in the real world, they don't have agency or they don't have good body ownership, probably the techniques can raise it beyond, I don't want to say normal, but the standard level, but raise it beyond my level. If I have in the real world very limited agency, then this could probably raise my score to give me more agency. And the interesting question is if I can transfer that back to the real world somehow.
So you're saying that because in the real world, in healthy condition at least, we are feeling most of the time a high feeling of agency.
Maybe.
But yeah, but that's the basis that we are, at least in healthy situations again, we experience high body ownership, high self-occasion, and high sense of agency. But again, there is no ground truth value that can be adapted. So we don't know if we are going to be feeling more agent after the experiment, for instance.
Can you do a pre-questionnaire about my feeling in the real world of agency, the post-questionnaire afterwards?
Well, we could do that. Actually, we didn't do that in this experiment, but this is an interesting question. If embodiment could increase this feeling.
Okay, thank you very much. So, okay, so we will move on to the next presenter. Thank you very much.
Thank you.
Okay, so first presentation is, could you relax in an artistic co-creative virtual reality experience? The authors are Julian Lome, Ronan Goni, and Valerie Granton. The presenter is Julian Lome? I don't know.
No, I'm Ronan Goni.
Ah, sorry. Okay, so please start when you get ready.
Okay. Hello. Doesn't work. Okay, so thank you. Good morning. I'm Ronan Goni from Érizeine in France. So I'm going to present this work done with Valérie Granton, who is in the room, and Julien Lome, who is an artist and a PhD student in Paris, France also. So I will try to answer this question. Could you relax in an artistic co-creative virtual reality experience? The contribution of the work is at 3 levels that will structure my presentation today. First, the design of an artwork virtual reality named Creative Harmony with a live performance and connected spectators. Second, a collaborative virtual environment that enable co-creation between performers and spectators. And last, an evaluation of the impact of the experience on the emotional state of connected spectators. So first, I begin with the artistic context of the work. So this is a picture of the scenography of the artwork. Creative Harmony proposes a peaceful universe with motion-based interaction with two performers, one dancer in an immersive space and one musician. Connected spectators, remotely connected spectators who interact with the performers to co-create a shared landscape. The experience Creative Harmony is structured in 3 successive scenes. First, a meditative introduction, then a co-creative phase, and finally, a shared contemplation of the resulting landscape. So the first scene is a dreamlike, peaceful representation of an undersea environment with some fantastic animals. You see a whale, there is a ray, a turtle with a closer view, swimming in the sea. In the second scene, the performer is now above the sea in a crepuscular atmosphere with fantastic flying islands. And he sees mountains growing from under the sea, and the avatars of the remotely connected spectators. So the avatars are are composed of the torso and the hands of the participants in a particle-based representation. On their side, the connected spectators are still in the undersea environment. They see growing mountains from the seabed, and they also see the avatars of the other connected spectators and of the performer, the dancer. In the last scene, all the participants and the performer are located in the undersea environment. They see all the avatars of each connected person. They see the co-created landscape and a fantastic ballet of particles around the avatar. So, sorry for the noise. So here you see the ballet of particles, maybe a little more. Okay, great. The ballet of particles that was built from a motion capture of real dancers. And you can hear also the music. It's an original composition for Creative Harmony. So now about the co-creation part of the experience. So it is related to the second scene. In the second scene, the motions of the dancer generates the shared landscape. You can see here the mountains growing according to the dance motion. Thank you. I have more music, so you can keep lower. Thank you. And on the participant part, some particle tracks that appears around the users invite to perform some gestures to follow the tracks. And when they follow the tracks, it provokes some modification of the landscape. So here you see the tracks and either the mountains grow or they decrease. Like here, we have several gestures to perform. Okay, so that was artistic content. Now about the relaxation in the artistic experience. So we conducted a study, a user study, on the connected spectators part, and with to validate three hypotheses. First, the creative harmony artistic experience has a positive impact on the emotional state of the connected spectators. Second, the users feel they are co-creating with other participants. And third, the participants experienced letting go and relaxation when immersed in creative harmony. So to validate this hypothesis, we used a standard psychological tool called BMIS. I will present it after, to evaluate the emotional state of the participant before and after the experience. And we used subjective questionnaires for the user experience evaluation after the experience. The apparatus of the experiment, we had one dancer in a large immersive platform called Immersia. Maybe you remember Anatole Écuyer presented this platform yesterday. And two remotely connected participants with HTC Vive Pro headsets. Thank you. Here is some videos of the experiment. The dancer in the middle, evolving in Immersia, and two participants with headsets following the gesture in the experiment. Okay, so about the evaluation of the emotion state of the user. So as I said, we use the BMIS tool, which for a brief mood introspection scale. So it is widely used in psychology and psychiatry to assess the emotional state of users, of patients. It evaluates the cognitive part of the emotional state. It is composed of 16 adjectives, 8 positive, 8 negative, that the user has to score with 4 different values to characterize its own emotional state. And from this evaluation, 4 indicators can be calculated: pleasant, unpleasant, arousal, calm, positive tirade, and negative relaxed, to more precisely characterize the emotional state of the user. For the questionnaire, it's quite standard. We had 19 questions with 7 Likert scales answers about general experience, body feeling, interaction, feedback, and collaboration, and letting go. About the experiment, we had 28 participants. The experiment lasted 40 minutes with 15 minutes of artistic experience. The result of the BMIS indicators demonstrate the increase of the emotional state for the indicators pleasant, unpleasant, and positive tirade, and a decrease of the negative relaxed indicators toward a more relaxed state. The fourth indicator was not conclusive statistically. So we can conclude for this measure that we had a feel-good impact on the users and relaxing impact on the user. So we can consider our first hypothesis validated, on the third one partially evaluated also. About the questionnaire for the two last hypotheses, unfortunately about the co-creation, it was not convincing at all. We had no co-creation feeling from the users because they focused on their own activity following the gestures, and they did not feel the co-creation. So maybe a lack of co-manipulation. We have to work on this part for later investigation. And about relaxation and letting go. So we already saw relaxation. But letting go, we had significant high scores for the 5 last questions about letting go in the questionnaire, and positive informal feedback on this part. So in conclusion, you saw creative harmony, an artistic environment in VR that enables a multiple users experience that connects the performer and remote spectators. We demonstrated that the experience has a positive impact on the emotional state of the connected spectators, with a relaxing effect and a feel-good effect. So I hope you will be able to try it one day. Thank you very much. And if you have any question.
Yes, thank you very much. So now Q&A session. Is there any question or comment? We have one, but this is related with third presenters. No question?
Thank you. I really want to try it. It seems really, really nice and really fun.
Thank you.
And just really beautiful. So I think that the artistic pieces are really nicely done, and seem very soothing, relaxing. The second questionnaire, is that yours, or was it validated somehow? Is it? I understand that the BEMIS is a standard tool, and how comfortable or confident are you in the second questionnaire?
Yes. So
it's always hard to make.
Yes. So it's our own questionnaire, of course, with a standard question from standard questionnaire on presence and usability, but it was mainly our own questionnaire, because Julien Lomez, the artist student, has an artistic intention with respect to the construction of his artworks. So we want to validate some particular effects, emotional effects on of his artwork with respect to the spectators. So he wanted to build his own specific questionnaire. So yes, it's very subjective to validate some hypotheses on this questionnaire.
And is letting go equal to relaxing?
No, but this is an open question, because letting go is a complex state of feeling, behavior, and it is why I did not check in green the last hypothesis we have. We have to investigate more what is letting go exactly. It's stronger than relaxation. It's not hypnotic state still, but yes, it has to still be more precisely defined.
Thank you very much. So unfortunately, we run out of time. So let's thank the speaker again. Okay. The next one is final presentation in this session. The presentation title is Exploring EEG Annotated Effective Animations in Virtual Reality, Suggestions for Improvement. The authors are Claudia Krogmeyer and Christos. Are you online? Okay, so please start when you get ready. Sorry. I misunderstood.
Hello, I'm Claudia. I'm from Purdue University, and today I'm going to be talking about our project titled Exploring EEG Annotated Affective Animations in Virtual Reality, Suggestions for Improvement. The goal of this study was to understand affective or emotional responses to virtual character animations which were presented to participants. They view these in virtual reality. So we looked at brain activity data, as well as their answers on a questionnaire to understand how they felt while viewing these animations. As a very quick overview, we used frontal alpha asymmetry or FAA measurements, which we calculated from EEG or brain activity data to understand objective emotional responses. Very generally, FAA refers to a difference between left and right prefrontal cortical activity. Previous research has shown that greater relative left activity has been associated with positive emotions and approach motivation, whereas greater relative right activity has been shown to be associated with negative emotions and withdrawal. Our work is a two-part investigation. So we had a preliminary data collection period as well as a primary study. In the preliminary data collection period, we presented a total of 12 virtual character animations. Ultimately, 6 of these were annotated with FAA data in the following primary study. Not only did we want to annotate these animations to use in this primary study, but we wanted to see would happy animations such as laughing or jumping elicit higher FAA than sad animations such as crying or feeling dejected. So the valence model of FAA, which proposes that positive emotions are associated with higher FAA, would predict that a happy animation would elicit higher FAA than a sad animation. In our primary study, we used these annotations in a 2x2 repeated measure study in which we looked at 2 levels. So we looked at annotated FAA, so previously annotated as low or high in the preliminary data collection, and character count. So 1 character again versus 4 characters. So that led us to 4 conditions. So 1 low, 1 high, 4 low, and 4 high. We wanted to see if we could replicate results from the preliminary data collection period concerning the 1 character conditions. We also wanted to look at the 4 characters to see how that might influence FAA measurements. And lastly, we also wanted to examine how self-reported positive affect might compare to the FAA measurements in this primary study. So this is a look at the 12 virtual character animations we annotated in the preliminary data collection. Participants were instructed to think about how they felt while viewing these animations. Each animation was displayed for their 6-second duration, and it was displayed 10 times, and they were, of course, randomized within the system. In between each animation, there was a 5-second interstimulus interval in which no animation was present. And we calculated FAA from these animation epochs in a standard way. Here is a look at the Emotive Epic X EEG headset. In the middle, you can see a participant wearing the Oculus Quest 1 modified to fit with this EEG headset. And then on the right, you can see those electrode placements. This is a look at our preliminary data collection findings. So we used one-tailed paired samples t-test to look at different pairs of animations. So here you can see the jumping animation did elicit significantly higher FAA than terrified, as well as than dance. We also looked at idle and laugh, and these do elicit higher FAA than terrified, but you can see not statistically significantly so. So considering our statistical results and the overall range, as well as the desire to want to create 4 character conditions with some level of variety, we ultimately annotated excited, jump, idle, laughing as high FAA, and terrified and dance as low FAA. In the primary study, we had all different participants. Like I said before, this was a 2x2 repeated measures ANOVA, in which we had the 1 character on the top and the 4 characters on the bottom. So 1 low is that 1 terrified that previously elicited low FAA. 1 high is the jumping. 4 low is 3 dancing and 1 terrified. 4 high is jumping, idle, excited, and laughing. We also wanted to understand how the self-reported positive affect would compare to FAA data. And we hypothesized that similar to the preliminary data collection, 1 low FAA would again elicit significantly lower FAA than 1 high, but the number of characters, so the 4 character scenes, was very exploratory. So these are our primary study findings. In this slide, we'll look at the top 4 lines of this table. So we actually found the opposite of the results that we got in preliminary data collection. So we found that 1 low actually elicited significantly higher FAA than 1 high. We did not find any differences between 1 low and 4 low, nor between 1 high and 4 high. When you look at the self-reported results, so this is the bottom 4 lines of this table, we do find what we would expect based on the preliminary data collection period. So we find that the 1 low animation elicited significantly lower positive affect than 1 high. And we also find additional results here. So we find that one low elicits lower self-reported positive affect than the four low. And when we look at one high, that actually elicits higher positive affect than 4 high. Well, when you look at them side by side, you can clearly see the opposite results concerning the one character conditions. You can also see that in both the brain activity and self-reported data, there aren't statistical differences between the 4 character conditions, but you do kind of see that trend of increasing positive affect from the 4 low to 4 high in both the brain activity and self-reported data. So as a summary, the primary study had unexpected effects. 1 low elicited higher FA than 1 high. And in self-reported, 1 high was higher than 1 low as expected. Additionally, 1 high was higher than 4 high. 1 low was lower than 4 low. And in both cases, we don't see a difference between the 4 character conditions. So these results, also considered with the participant commentary, really seem to say that the 1 character conditions are at the very least more salient in terms of either their emotional effect, the way that they're perceived, the way that they're interpreted. So I put a few of the participant comments here. So you can see several people, and there were a lot more not placed here, but you can see that people found the 1 character condition just more clearly interpretable, obviously excited, more impactful. And then someone also said the multiple character scenes, so the 4 character scenes, were more confusing than anything else because there's different animations and they didn't know which character to look at first. So previous research has shown that participants respond differently to one versus groups of emotional characters. We think that it's very likely that unexpected contextual effects arose from these 4 character conditions, changing the meaning of those scenes, which we couldn't predict despite our FA annotations of the individual characters. Some participants mentioned thinking of these 4 character scenes more like stories, so that's going to vary a lot between people. We also know that FAA can increase during reappraisal of negative image viewing. So if we consider that participants maybe thought differently about the 1 character scenes based on how they had thought about those individual characters in the 4 character scenes, this may have really changed how they thought about the 1 character scenes. So we think effects from the 4 character scenes likely bled into the 1 character scenes. We have a lot of suggestions for future directions, but there's just a handful here. So we did go with a very plain environment, very simple mannequin characters with no facial expression. We really wanted to look at the emotional output of these virtual character animations, but in our future work, we would strongly suggest just having virtual characters, trying to control for any uncanny valley effect, having a furnished environment, so just making it more interesting for the user rather than trying to isolate a single factor. It would be important to consider the influence of character groups on emotional context, as in our case, it seems to have changed FAA in unexpected ways. And even though it seems like a simple change going from 1 character to 4 characters, we might recommend starting with groups of 2. And rather than looking at different animations, so for example, rather than looking at 1 low FAA and another low FAA, that's a different animation, keep them the same, because that can also be a different variable. And lastly, there is not a universally accepted model of FAA. A lot of previous VR emotion studies have used FAA as a correlate of emotion, which is essentially what we do here. But it can also be seen as a marker of motivation or even effortful control of emotions. So it's likely that FAA was not the most appropriate thing to look at in this case. So as one last takeaway, we would suggest considering how seemingly small changes, like going from 1 character to 4 characters, might have very unexpected effects on perception and emotion, especially when you're looking at brain activity data. So thank you very much for listening. And if you have any questions, I will attempt to answer.
Thank you very much. So Q&A session. Is there any question or comment?
Thanks very much. This was really nice. I have a question mainly about your motivation, because animations don't happen in a vacuum. So typically there's a story or there's a context to something. And your point at the end about how the four were not really coordinated, it seemed, if I'm right, they didn't seem to be all sad because an event happened or they were consoling each other or something like that. It was just four independently valenced animations that were put together. Is that right?
Yeah. And so, I mean, your point is great. And yeah, so for example, the three dancing and the one terrified, you can't just put them together and assume that doesn't mean something new. But yeah, at the time we were just trying to keep it very simple. But yeah, I think it would have been much better overall had we actually decided to go full force into the story direction. And that ultimately was the motivation for me. I'm interested in the future working on very targeted affective experiences. So it would probably just be better studied in a more complex environment. So it probably was not good to make it so simple.
Yeah, and the theater, you can learn a lot from theater and over exaggeration of things in theater on a stage, for example. There's lots of really effective ways to kind of over accentuate what's going on to try and elicit certain emotions. So the stage is a good place probably to start, I think, in trying to come up with these animations. Or yeah.
Thank you.
Very much. Any question or comment? So I have a simple question. So as I understand, so in the first re-experiment, so the idle case is the second highest FA value, right?
I'm sorry.
So the first, so the highest FA value is jump, and the second one is idle.
Yes.
So could you explain? Could you elaborate on the reason for that?
Yeah, that's also one thing we mention in the paper. We don't propose to understand why these elicit these specific responses. Some of them make more sense, like jumping is happier than terrified. Some are very obvious. But I mean, it's also possible that just where they were on the screen can influence the brain activity as well. So idle may have just been more positively perceived just because it wasn't negatively perceived. And we didn't tell people it was idle. It could have just looked like a happy stance. But that is another limitation. We would need to understand these annotations much better.
Okay, I understand. Thank you very much. Any question? Any very quick question? Okay, we almost run out of time. Okay, let's thank the speaker again. Thank you very much. Okay, so now I will close this session. So I would like to thank all the speakers and participants who participated in this Q&A session. Thank you very much. Okay, so please enjoy lunchtime and remaining session as well.
Next session, paper session 4. So, okay, so we will start paper session 4. So sorry, I'm Toshiyuki Amano from Wakayama University. I'll be chairing this session. So the next session is related to the display rendering technique. So we have 3 papers. The first paper is rendering method of microdisplay image to expand pupil movable region with an artifact for lensed array near eye displays. So the presenter is Yuichi Fujimoto, Takeshi Sabe, Masayuki Kambara, and Gert Rutenberg, Hirokazu Kato. Please start.
Okay. Good afternoon, professors and researchers. My name is Bi. I come from Nala Institute of Science and Technology. I'm a student of Interactive Media Design Lab. My topic is a rendering method of microdisplay image to expand pupil mobile region without artifacts for lens-light linear displays. Currently, we are with a big box on user's face. This kind of device are thin and heavy that prevent users use them for a long time. But two outstanding models have solved this kind of problem. NVIDIA prototype and Seoul National prototype. But their prototype eye reliefs are longer than 20 millimeter. But sunglasses eye relief is from 10 millimeter to 20 millimeter. In addition, they didn't consider the effect of pupil size and visual perception on image quality. This is the principle of lens-light linear eye displays. WE is the eye box in which users can see a clear virtual image without artifact. When we considering pupil size and visual perception, PSNR is used to evaluate the quality of retina images. When pupil move inside the eye box, no artifact on the retina image, so the PSNR value is infinity. When pupil move a little bit out of the eye box, artifact will appear on the retina image. So the PSNR value will decrease from infinity. In our previous research, we have already verified when PSNR value larger than 50 in traditional method, even there is artifact, but due to human visual perception limitation, we can't perceive the artifact. If pupil continue move out of the eye box, PSNR value will continue decrease. So we can begin to see the artifact on the retina image. If pupil continue move out of the eye box, the PSNR value will decrease. So it means the intensity of the artifact on the retina image is increased. Based on this principle, we defined practical pupil mobile region, PPMR, as a new matrix considering pupil size and visual perception, in which no artifact can be perceived. PMR, pupil mobile region, means the pupil move inside the eye box. The value of PMR is equals to eye box minus pupil size. If eye box is 20 millimeter for a pupil size of 4 millimeter, PMR is 16 millimeter. This value of PMR is enough for a VR prototype, but actually for lens-light linear eye display, the eye box is much smaller than 20 millimeter. So we have to consider human visual perception. So we defined PPMR instead of eye box in lens-light linear eye displays. This is the basic thinking of enlarging PPMR. The left figure is the PSNR value changes following pupil size, and the red figure is the PSNR value changes following pupil transition distance from the microdisplay center. For a lens-light linear eye display, the eye box, when the eye box is 4.5 millimeter, when the pupil range from 2 millimeter to 8 millimeter, the pupil size larger than the eye box, the
the PSNR value will decrease quickly. Or when the pupil size transition makes the pupil out of the eyebox, we can see the black curve. The PSNR value also decrease very quickly. The red curve is expected rendering method. We can see the robustness of expected rendering method is stronger than traditional rendering method. Typically, value of PSNR for lossy images are from 30 to 50. Different types of noise correspond to different PSNR values. The PSNR threshold for expected rendering method is Y. This value we will be discussed in the next slide. This is the principle of rendering microdisplay image. In this process, we not only considering pupil size, but also we define a new parameter as pupil margin as the gray part, as this gray part show. This pixel value for a randomly pixel A on microdisplay image, its value depends on the pixels on virtual image plane. The light of pixel A emit from each lens go to the pupil plane. Some lights go into the pupil and the pupil plane. Others go out of the pupil and the pupil plane. So we can calculate the intersection area between the light with the pupil and the pupil margin. For example, the light of pixel A through lens 6 go out of the pupil and the pupil margin. So the value of V6 the value of V6 on this virtual plane, the weight is 0. The light of pixel A goes through lens 7. The intersection area is S7. The same principle, we can calculate S8, 9, and 10. Finally, the weight of V7 equals to S7 divided into the sum of the light go into pupil and the pupil margin. So after we calculate all the values on the micro display, we can get a micro display image as shown in image 3. This is our image 3 is rendering by our method. Image 1 is input image. Image 2 is micro display image rendering by traditional method. So we can see the difference between our micro display image and the traditional micro display image. In the traditional micro display image, we can clearly see the boundary of each elemental image. But in our micro display image, this concept is disappear. The first line is rendering by traditional method, and the third line is rendering by our method. In the condition of same transition distance, let us compare the same transition distance. Our method PSNR is larger than traditional method. So this means the intensity of artifact in our method is weaker than traditional method. So from left to right, we can see the intensity of the artifact is increased. So when PSNR value is larger than 40, so we can't perceive the artifact. When PSNR smaller than 40, we began to perceive the artifact. So we set the threshold of PSNR is 40 in our rendering method. In order to compare the difference between traditional method and our method, we calculate the error between the retina image with the ideal retina image, like this lane and this lane. So we can compare the difference. This is the PSNR curve with different pupil margin. When the pupil margin is 0.8 millimeter, the PPMR value is the largest. So finally, we set the pupil margin is 0.8 millimeter. This is our hardware. The glasses frame is printed using 3D printer, and the driver board comes from a Sony HMD. All the programs were implemented in C++ with an OpenGL on a Ubuntu system. In order to verify the effect of our method, we capture images using a Sony camera. The aperture of this camera can be adjusted. So let us see the traditional method. When pupil size enlarge from 4.4 millimeter to 6.2 millimeter, the artifact will appear on the image. But in our method, this artifact is disappear. Even when we decrease the eye relief to 10 millimeter, when the pupil size is 4.4 millimeter, in traditional method, the artifact can be perceived, but in our method, this artifact also disappeared. This is the different transition distance from the center of the display. In the traditional method, when the pupil move from the center become larger, the artifact is disappear in the figure 2 and the figure 3. But in our method, this kind of artifact is disappeared. This is a video about our rendering method combined with eye tracking. It can tolerate faster eye rotation speed. We proposed a rendering method for micro display images that takes pupil size into account and include the idea of pupil margin in the retracking process. Through the experiment, we verified our method can enlarge PPMR to accumulate large pupil size and wide transition distances. It can reduce eye relief to an optimal distance of 10 millimeter. In addition, our rendering method combined with eye tracking can tolerate a faster rotation eye. Thank you for your time.
Thank you. Is there any question from audience? No? Okay, so I have a question. So I think that the pupil size affects so perceptual illumination, but also it also affects so maybe it makes some blurring by the crosstalk. Did you consider about that? Maybe if the pupil size is enlarged, next pixel is coming in and it makes some crosstalk.
So that's a reason we define a new parameter of pupil margin. So when pupils, even for our method, when pupil size range from 4 millimeter to 6 millimeter, no artifact can be perceived. But if the pupil size continue enlarge, our algorithm also can be perceived artifact. So, but this is but this problem also can be changed if we change the lens light array parameter. But for the different transition distance from the center to the boundary of the display, when the transition distance is become larger, also artifact can be appeared in our algorithm. So that's why we want to combine with eye tracker to eliminate artifact.
Okay, thank you. Is there any question? No? Okay, so I apologize. Actually, so each presentation has 15 minutes, 12 minutes for the presentation and 3 minutes for the question. So it also run out of time. So we will move to the next session. Okay, thank you. The next talk is characteristics of background color shift posed by the optical see-through head-mount displays. The authors are Daichi Hirobe, Yuki Uranishi, Jason Olsky, Shizuka Shirai, sorry, I can't pronounce. Ratsi and Haruo Takemura. Presenter is Daichi Hiroe. Okay, so please start.
Okay, thank you for introducing. Hello, everyone. My name is Daichi Hirobe from Moscow University. Today, I want to talk about this topic. First, optical see-through head-mount displays, or HMDs for short, are often used for AR and overlay digital content directly onto the user's view to support work that requires simultaneous viewing of both real and digital information. However, some problems still have to be solved before these displays can be used in a wide range of situations. One of these issues is that the colorable light from the display is blended with the light from the background. This may cause poor content visibility or lead to incorrect operation, because colors that the users perceive are different from those the developers intended. In order to address this problem, color compensation methods have been widely studied. Color compensation methods subtract background color from content color and make blended color desirable one. For example, when you want to show color yellow to a user on a green background, if you display yellow, it blends with green and it is seen as light green by user. But if you display red, it blends with green and the user sees yellow correctly. This is a summary of color compensation. Precise color compensation requires to know background color precisely. However, optics of an OHMD is not completely transparent, and the background color a user sees is shifted from original one. So we studied about background color shifts caused by OHMDs. We introduced two related works here. First is a study about color compensation method by Hincapella-Moss et al. They propose color compensation methods utilizing binary search, which can be executed in real time. They try to address background color shifts by linear regression. It matches well, but there is an error in some situations. Authors also stated that linear regression is only one possible approach. Second is a study focused on background color estimation by Liu et al. They try to estimate background color using linear regression in XYZ color space, and they evaluated their estimation results in terms of hue difference, delta H, and perceptual difference, delta E. The estimation is good for hue difference, but there are big perceptual difference for some colors. Currently, previous studies about how background color shifts are insufficient, and many studies support that the background color is shifted uniformly across the display, but it is not sure. In addition, they don't consider how viewing angle affects the background color. Given these situations, we studied about background color shifts in some aspects. In detail, we studied about these 3 research questions and investigated how optics of OHTMDs shifts the background color and how positions in a display or viewing angle affect the shift of the background color. To answer these questions, we measured light from background under many conditions. We used 3 off-the-shelf OHTMDs, Magic Leap 1, and HoloLens 1 and HoloLens 2 as measuring targets. Then I describe about measurement settings. We printed measuring instruments using a 3D printer. Red parts are fixtures for an OHTMD, and green parts are fixtures for a spectrometer. By fixing them separately, we could remove an OHTMD without moving a spectrometer, so we could measure same background light directly and through an OHTMD. A purple part is a mask which limits the measuring area of an OHTMD. We divided the display of each OHTMDs into 9 areas, so we printed 9 masks corresponding to each areas. Yellow parts are the bases of a spectrometer. We printed 3 different heights of bases to change measuring angle vertically by raising or lowering a spectrometer. We named each bases low, normal, and high. We used low and high only for measurements in center area. This middle picture is an actual setting used for measurements. We used certain kinds of colored paper as a background, and LED lights which have a broad spectrum distribution as light sources. Background paper is supported by instruments printed by a 3D printer as well. Measuring conditions are determined by 3 factors: background colors, measuring areas or angle, and target OHTMDs. We prepared 13 background colors, and we measured for 9 measuring areas and 2 additional measuring angles for the center area. Our measuring targets are 3 OHTMDs. So we measured background light in 489 measuring conditions in total. To answer research questions, we analyzed measuring results. For research question 1, we compared directly measured background light and background light measured through an OHTMD. We used CI delta E 2000 as an evaluation index. What we measure is the spectrum of background light, but LAB color can be calculated from measured spectrum. So we could calculate delta E directly, delta E between directly measured background color and background color measured through an OHTMD. We refer delta E between these 2 colors as delta EDH, and the threshold of CI delta E 2000 is 1. So if delta EDH is greater than 1, it means that the background color is shifted by an OHTMDs. Left table shows averages of delta EDH for all 9 measuring areas of all OHTMDs. By looking at this table, it can be said that every OHTMD shifts background color perceptibly enough amount. This result means that the shift of the background color should be considered for color compensation. And also, right graph shows averages of delta EDH for all background colors. This indicates some background colors shift greatly, while some others don't shift so much. So we found that there are variable colors and relatively constant colors. For research question 2 and 3, it is required to compare how the background color shifts between 2 measuring areas or angles. For example, comparing how the background color shifts between 2 different measuring areas is required for research question 2. However, it's hard to write the background uniformly. So comparing measuring results of 2 different parts of background is unfair. Then we compare the spectral transmittance of these measuring conditions instead. We calculated the spectral transmittance of each measuring conditions by dividing spectrum of white color measured through OHTMD by directly measured spectrum of white color. The reason we use the white color for calculation of spectral transmittance is that it has the broadest spectrum distribution of all background colors. Then for research question 2, we compare the spectral transmittance of 2 measuring areas. We applied two spectral transmittance to the same directly measured background light spectrum and got two colors, C-calc and C-calc dash. We refer delta E between these two colors as delta E CC dash and use this as an evaluation index of research question 2. We used spectral transmittance of center area, area C, as a baseline, and we compared area C and each other measuring areas except C. These below tables show delta ECC dash of each measuring areas for each OSHMDs. There are some areas whose delta E is greater than 1 for all OSHMDs. So it can be said that how the background color shifts differs between areas. This result implies that where content is displayed should be considered for precise color compensation. We use delta ECC dash for research question 3 as well. We compared spectral transmittance of two different measuring angles. We used spectral transmittance of normal position as a baseline and compared spectral transmittance of high position or low position. The table below shows delta ECC dash of high and low for each OSHMDs. This indicates that for magic leap 1 and HoloLens 2, measuring angle affects how the background color shifts. This result implies that viewing angle should be considered for precise color compensation when using these OSHMDs. We also evaluated the measuring accuracy itself. We evaluated the accuracy of spectral transmittance measurement. We compared CHMD, background color measured through CHMD, and C-calc background color calculated using spectral transmittance. We calculated spectral transmittance using only measurements of white color, so there are some errors between CHMD and C-calc of other colors. We refer delta E between CHMD and C-calc as delta EHC. If spectral transmittance is measured with sufficient accuracy, C-calc should be close to CHMD, and delta EHC should be small enough. We plotted the results of each measuring conditions in graph below. Vertical axis is delta EHC. Horizontal axis is illuminance of background light measured through an OSHMD. This indicates that when illuminance is low, delta E is high. It means that if measuring accuracy, if background illuminance is low, measuring accuracy is low too. But percentage of data whose delta is lower than 1 is 86% when using data whose illuminance is greater than 10 lux only. So it can be said that if illuminance is sufficient, measuring accuracy is sufficient too. In conclusion, we studied about shift of the background color caused by OSHMDs. In detail, we studied about 3 research questions and investigated how optics of OSHMDs shifts the background color and how positions in a display or viewing angle affect the shift of the background color. For research question 1, we found that background color is shifted perceptibly by all OSHMDs, and some background colors shift greater than other colors. For research question 2, we found that shift of the background color is not uniform for all OSHMDs. For research question 3, we found that viewing angle affects for Magic Leap 1 and HoloLens 2. Then we introduced 2 future works. First is measuring again with stronger light source, because when the luminance of background light is low, measuring accuracy is low too. Second is subjective measurement about how the background color shifts or how it affects usability. In this study, we measured background colors objectively, but it should be studied subjectively too for more practical analysis. Especially, subjective measurement with more complex background or more complex lighting conditions are needed in order to know how the background color shifts in real situations. That's all. Thank you for listening.
Thank you. Is there any question from audience? Oh, no? Okay, so I have a question. So,
Yes.
Did you consider about the perceptual things? So I think that we have a color constancy. So that if the color shift is occurred for the same direction, so maybe all color going to a reddish.
Yes.
Maybe it is not a matter for that.
Yes. That may be correct. So in this study, we only objectively measured, so we don't consider such any subjective properties. So we this subjective measurement about how the background color shifts. This is also future works. Yes.
Yeah, I mean so that that all color is changing to reddish.
Yes.
So we might think that it is so the illuminated red illumination. So that maybe we can understand the correct color. So in that case, we have no need to the correct display color. I think so.
Yes, that might be true. So if we do some subjective measurement, such background color shifts are not a problem. Maybe so we may be able to get such results. So yeah, but in this study we only do objective measurements. So yeah, so we don't know. Yeah.
Okay, thank you. Any other question?
Thank you for the presentations. So my question is, what do you suggest to do as on how to compensate the color shifts?
So I asking about how to use this result for color compensation.
Yeah.
Okay. So to be honest, I don't consider such more practical use case in these times. But in this study, we found that position of the display or viewing angle should be considered for color compensation. So more practical color compensation method which considered such results can be considered. Yes.
Yeah, I ask this because I know like simple compensation methods doesn't really work due to like color dispersion problems in waveguide itself, from my understanding. So yeah. No, thank you.
Thank you.
Okay, so any other question? Okay.
As far as I know, the HoloLens use sequentially changing color to project the images, right? So red, blue, or I'm not sure about the exact order, but I guess the exposure time to measure the color shift will be affected by the let's say the time duration of the exposure time. Sorry about that. So my question is, did you consider the sequential change in colors when you measure the HoloLens 2 or 1 device?
We measured the HoloLens 1 and HoloLens 2. We measured for both.
So I'm saying that the HoloLens project at one time one color, right? And then change it to another color, change it to another color. So exposure time, within the exposure time, you may have 3 colors evenly, or 4 color. I mean, you will have another color additionally. So that can affect your result, right?
We measured in same exposure time for every measuring conditions.
All right. Okay, so we run out of time. So let's thank you, speaker.
Thank you.
Okay, we'll move on the last talk in this session. The title is tiles user customize the broad display using omnidirectional camera projector system. Also, Jana Forfart.
Shio Miyafuji, Jefferson Padram, Toshiki Sato, and Hideki Koike. So the presenter is Yana Hoffert. Okay. Please go ahead. Please go ahead.
Thank you very much. Yeah, welcome to this presentation of OmniTiles, a user customizable display using an omnidirectional camera projector system. My name is Jana Hoffert from the Tokyo Institute of Technology, and together with my co-authors, I would like to introduce our interface to you. So OmniTiles is a manually shape-changing display targeted towards families with children. We use a single tiles that can be connected via magnets to more complex shapes, but also be used on their own. For the information display, we use a camera projector setup, but later a bit more on that. So for now, why did we choose this kind of setup instead of a higher quality HD display that could provide more functionalities even? So the answer to that has to do with the sturdiness of common displays, or rather with their fragile nature. I think most people, and parents in particular, know this image. Some people here in the audience might even have a device with the Spiderweb app right now in their pockets. So the thing is, while adults usually try to handle their devices responsibly and some accidents occur, children act more out of curiosity, which often means not using a device as intended. Therefore, devices for children should be designed with some additional points in mind. First, they should be safe for both the child, but also for the device. And this is actually achieved by using sturdy materials and either no automatically moving parts or parts that only move with a low force. Next, their protection and maintenance should be realized at a low price. So in case that something breaks, it doesn't really matter that much. And finally, as kind of as a nice to have, they should offer as much physical interaction as possible for an increased engagement. And this led us to our OmniTiles system, and where the tiles can be used on their own, but also in structures or as information carriers, as we will see a bit later. So the tiles themselves are created from a durable 3D printed material, which allows a fast and low-cost production. The magnetic connections of the tiles allow to connect and disconnect them as the user wants without any parts that could move on their own. Our camera projector setup can track the tiles and display information onto them. This has the advantage that we do not need any batteries for the single tiles, and the only fragile parts are the camera and the projector, which are ideally hidden underneath the table where the system is placed on. This way, the tiles can be thrown around and nothing really breaks, except for maybe things in the environment. So, all right, main inspiration and related work, besides the obvious reference to the McFormer's toy, consists of 3 types of systems. Systems specifically targeted towards children, which usually consist of sturdy toys where some sensors have been integrated. Then 3D displays and shape-changing displays, which offer more functions but require a responsible handling due to their fragile parts, which are therefore not really suited for children. And last but not least, different kinds of projection-based systems, as we wanted to avoid conventional displays. Furthermore, we looked into different kinds of tracking, and more precisely into tracking via infrared markers, since they offer nice tracking possibilities without being noticed by the user. Our main inspiration was Narita's work here on the right-hand side, which uses dot patterns dot patterns that are arranged in a matrix to detect and track deformable material. We adapted this for our needs. And this led us to the following system. Our system builds mostly on the setup of Takagi's work, which uses a projector and an infrared camera underneath a wide-angle fisheye lens to track the environment and project onto it. Now, Takagi used retroreflective markers while we are using our new tile system, since retroreflective markers come with some disadvantages. To improve the light conditions in both systems, we use a ring of infrared lights around the fisheye lens to improve the light conditions. Also, we use Python to track our system and Unity for the application and image instantiation. So to produce the tiles, we first print out a model. In this example, a simple square and a smaller size square. And in this prototype version, on the edges, there are some pockets into which the magnets can fit in. To save material and time during the production, we made the projection space a bit thinner than the edges so that we would just save on the material there. We then apply a matte spray after covering dots for the tracking, which I will explain here and after. To further improve the tracking, we draw like a thin black line around the projection space, just to be able to like clearly identify the shape of the tiles. Okay. Oh. There's a picture missing, sorry. So our tile detection starts with an adaptive Gaussian threshold on our camera image, which is in grayscale. On that, we use OpenCV's contour detection to find close contours. We then calculate the circularity of these contours to determine the shape of the tile and the expected number of group dots. To find sad dots, we use then OpenCV's blob detector and only keep the ones within the located contour. So our tile recognition is based on the group dots that are placed around the edge on the projecting area. Starting at 0 degrees of a coordinate system, the number of the dots provides a unique asymmetric array, which we use to determine the tile, its rotation and orientation. So in this example, we have here like 1 dot, 1 dot, 1 dot, and 3 dots, and so on. And this gives us this resulting ID array. Additionally, we also calculate the angle difference between the center of the group dots so that we can use it for error detection. For example, for a square, like in this case, the center should ideally be placed apart. By 45 degrees. So we use the circumstance to detect false positives and occlusions, as we know the ideal length of an ID array. For example, when a false positive occurs, like here, the brown dot, the angular distance to the neighboring dot groups is far less than the expected 45 degrees. So hence we know that this brown dot is the most likely to be wrongly detected, and we can delete it from the array. In a similar way, we can detect occlusions if the angle difference is too high. Sorry. And once we detected an ID array, we can compare it to our stored library of arrays and select the one with the most identical entries to be our most likely tile. Furthermore, we store information on previously detected tiles, including their location. So we assume for this that the position of a tile in 2 consecutive frames will not change too much. So we can then compare the number of identical entries and take the ID which has a higher number, since that should be the correct one. So this is more like in case some new occlusion or some new false positive occurs. And we then determine the rotation from the shifts in entries between the detected and the library tile. Oh, and this provides some interesting interactions, since with this we can not only recognize a tile that leaves and re-enters the tracking area, but we also know its front and back side and its orientation. Therefore, we have these 4 basic interactions. 3 of these can be performed with a single tile marked here in blue, while the last one marked in orange is the connecting and disconnecting interaction between 2 tiles. By combining these 4 simple base interactions, more complex behavior for single tiles and structures of tiles can be modeled. Here. Okay.
Oh, one.
Sound sensitive. So here we implemented an example application for the language learning. On the left is a single tile which displays a kanji and the corresponding image of that kanji for the learning. And on the right-hand side are 2 words or 2 kanjis which combined give a new word. In this case, white and bird, which becomes swan in Japanese. So for an additional input possibility, we designed an external infrared LED light that is also tracked by the camera. It can be activated via the button on the side, and it can be used as a pointer-like input. So this can then be used to create different applications like drawing on the tiles. Here we created 2 applications. one which uses different colors and one which exchanges the dominant color for a different texture. The color information can afterward be used for additional functionalities, like in this case, where we use the drawing and the arrangement possibilities of our system to create a customized map for a simple space shooter. The user can draw obstacles and other grounds like speed fields onto the structure that will block or speed up the player. Though even after starting the game, the user can still change the map by simply reorganizing the tiles, since the system stores the information of the tiles and what was drawn onto them. So they can even eliminate or move the player around by removing or picking up the tile and carrying it around. Yes. So in the future, we would like to extend our system by using different materials that allow us to deal with current self-occlusion of the tiles. For this, we could use half mirrors or PDLC foil. Also, other materials could be used to further adapt the system to the user's needs. And of course, we would like to finally conduct a user study with children to get some feedback of how they actually like the system and how they really interact with it. So, and this concludes our presentation. We hope that with this robust shape-changing system that allows for complex shapes and a rigorous handling, we can provide a fun interaction for people of different generations who want to customize their system in a playful way to their needs. Thank you very much for your attention. Any questions?
Thank you for presentation. Okay, so do you have any question from audience? No? Okay.
A short question. Do you have a plan to make it touch sensitive?
Make it touch? Yes,
sensitive,
we
yeah.
already looked into related work, which also has propositions of how to make especially 3D printed tile touch sensitive. And we are currently thinking about using also like the camera input to detect the finger of the user on the surface. So
Okay.
yes, that's definitely something we're trying.
Just a short comment about that. Not only the finger touch sensitive, but kids tend to touch this kind of surface by not only the fingertips,
Yeah,
but also your
hand.
So,
Yes,
so is there any chance to detect such kind of large blob-sized touch detection?
We do hope so, because currently the camera image can actually see like if there's like a real contact, not just like in the air above, but like a real contact on the surface, you can actually see the hand through.
Yeah,
so we're currently trying with like different filters and stuff to get a nice image of the hand and use that.
Nice to hear. Thank you.
Thank you.
Any other question?
Thank you for the talk. So I think that one of the questions I have about is, it seems that the display is bended in different degrees, and something that I'm concerned about is the light sources from maybe, say, the flashlight, or even from the, I would say, the light from the settings. That does it actually affect how does the user would see the display in all of the different degrees? I mean, the surface have with a different reflections on it.
So the projection degree, not so much, except for like the really out far borders, because the projection space itself comes down to what angle the fisheye lens over the projector can project onto. So for this system, we used one that can project around 120 degrees. So that's kind of our projection range. And below that, it's kind of dark, which is the reason why we actually often have these small tiles underneath, because they are not projected onto, because the angle of the fisheye lens won't reach it. Besides that, the projection quality like within that range doesn't change much. It changes a lot though with the ambient light of the environment. So if it's like a really bright setup, then the projection isn't seen that clearly.
Thank you.
Thank you.
Any other question? Okay, so I have a question. So
Yes.
I'm wondering how to expand this method to the free form shape. So maybe you can employ some sort of cylindrical surface or sphere surface for the tile. Is this possible?
How do you mean exactly? Like
in the surface, curved surface for the type.
Oh, like a curved one.
Yeah.
Ah, okay. Yeah, actually, I think that should be possible. Like currently, we are also exploring a bit into automatically moving parts of softer materials. So they kind of like bend around and go straight again. So yeah, since we're only relying on the dots, that's definitely possible.
Okay, interesting. Any other question? No? Okay, so we finished all three presentations. So let's thank speakers again. Okay. I'm not sure, but we have a break for. Okay, so sorry, we have break for until 40:30, I think. Next session is a poster session. It will start 40:30 at the poster session room, I think. Thank you.
And sorry, everyone, just before you go, so we have a poster and the demo sessions that will be run concurrently in about 10 minutes time. So if you navigate on the stairs just right outside to your left, and you should be able to see the demo room right in front of you. And if you make another turn, maybe just right behind you or behind the wall, whatever it is, that will be the poster room. So feel free to have a look, and that should be run for an hour and a half before we have our next keynote speech. Thank you.
Okay, thank you very much. So I'm presenting research called Identifying Language-Induced Mental Load from iBehaviors in Virtual Reality. So we basically designed a simple virtual environment and took information from psychology research about how your eye metrics change depending on your cognitive load. So for one of the most famous is that the pupil size is getting larger. And we were specifically interested in if people might look through the wall if they're thinking about something. So we call that focus offset. And so we had several samples of speech presented to users, and they were basically trying to comprehend their native language and then a language that a foreign language. And we were expecting that the foreign language triggers more mental load. And we used this language task because then people are like show free gaze behavior and are not using their gaze to do a specific task, but looking around naturally. And so in this situation, looking around naturally, hearing different samples, we analyzed it, and we had 4 samples. And the interesting thing is we noticed an effect, but this effect was strongest for the second most difficult sample, not for the most difficult one. And we were able to show this effect in pupil size, of course, that was the easiest. But also we got a significant effect in this looking through surfaces, although that followed less the pattern of pupil size, so we need to investigate that further. And we were able to show less fixations while concentrating. So we want to evaluate this focus offset metric a little more in the future. Thank you very much for listening.
Thank you. So I have a quick questions for you. So what sort of the future works that you are trying to go for? Is there any particular directions that you thought your work will be able to contribute to the future in a way that, I mean, in the scope of the research topics that you are currently focusing on?
Yeah. Yeah, thank you very much for the question. So, of course, the focus offset, like not directly focusing on the surface, is quite interesting. It hasn't been examined in virtual reality very much, especially because it's very difficult to calculate. It's quite unstable. So of course, I would like to investigate that more, but we need to remember that there might not be an actual relation to cognitive load. So I want to look at many other eye metrics, like the fixations were calculated in a not the most ideal way in this research. So I want to, for example, make it easier to have a tool which detects, is good at detecting fixations from the 3D gaze rays. Most tools do that for a screen scenario. But also, what can we say about cognitive state in virtual reality? Let's say like the general research. So for example, attention, we had some other papers doing that. Yeah, I think it's helpful for that, especially how to analyze the gaze information. Okay, thank you very much.
Yes, thank you very much for your talk and presentations. Thank you. Yep, so let's move on to the next presentation. Yep, so now we have the interview sessions for the next poster, which is the evaluations of predatory presentations of the conducting motions using tactile sensation for the visually impaired poster, which can be actually a long poster, but yet we will have the author to present their work. And please.
Hello, my name is Yuto Ueda from Keio University in Japan. My research is trajectory presentation of conducting motions using tactile sensation for the visually impaired. I enjoy playing bassoon. A bassoon is a woodwind instrument, and I want to play with various people, but there is no visually impaired people in orchestra I belong to. So the reason, I guess the reason is that they feel a barrier to participate in orchestra because they can not see the conductor's motion like this. So I want to help them. So so we propose a method of presenting conducting motion and tactile using multiple vibration actuators. So I conducted a quantitative evaluation to compare the baseline and my proposal method. So baseline is a point presentation. Point presentation is a method in which a single vibration actuator is vibrated in accordance with the timing of beats. So I use reaction time as evaluation metrics, and the results show my proposal method is better than a baseline method in some condition. Yeah, that's all.
Thank you very much. So a quick question for you. Do you have any future directions, or did you think that how can this will be help not only for the people with the visual impaired, or maybe for any other general use cases?
General use case.
Yes.
Okay. And I want to play them in orchestra. So so they feel the trajectory from them back. So, and they feel the conductor conducting motion. So we can play in orchestra with and them. Yeah, that is use case.
All right, that's definitely very interesting. Thank you very much. Yes, thanks again. So let's move on to the next poster. Yep, so here we have our next poster, which is for the AR FPS game using static and dynamic physical obstacles. And we would like to have our poster authors to quickly run through with their poster and the contents.
Hi, we propose AR FPS game using static and dynamic physical obstacles. Here is an introduction. Existing studies propose VR and AR games to promote exercise, support running, and support rehabilitation. To enhance the immersive experience, VR experiences using physical environment have been proposed. Therefore, we propose highly immersive AR games using physical obstacles. In order for the players to enjoy exercising, we choose first-person shooting as our game. AR is used instead of VR because it is easier for players to recognize the real space. The proposed game is a game in which a player becomes a character in the game, avoiding enemy attacks and defeating enemies that appear around him or her. In order to avoid enemy attacks, the player needs to take action using physical obstacle in the surroundings environment. In this game, physical obstacles are classified into two categories, static and dynamic obstacles. Static obstacles include things that cannot move, such as walls. Dynamic obstacles include things that can move. Here is the example of game design. For example, object placement considering real space. An enemy attacking a player over an obstacle with a grenade. Hiding behind a physical obstacle to prevent enemy attacks. Implementation. Horrendous and Unity were used for implementation. Static obstacles were recognized using scene understanding. Dynamic obstacles were recognized using depth cameras built in Horrendous 2. We evaluated the game itself and the contribution from the use of real space. Each of the 14 participants played the game for 3 minutes and answered the questionnaire. Both game itself and contribution from the use of real space were highly evaluated. But some items low and comments from participants pointed that to be improved. Thank you for attention.
Thank you for your quick descriptions. So I have a quick questions for you. So have you ever considered any use cases for the outdoors? Maybe because since AR or maybe HoloLens could be one of the device when, for example, if you want to use it on the outside and there are some sunlight that can hinder the effect of the AR markers or the cues.
Sorry, please. More please.
Yes. So technically speaking, so have you ever considered implementing the prototype on the outdoor with their very bright sunlights? Yes.
This game, I consider play outside, but this system is need physical obstacles. So the scene understanding cannot recognize physical obstacle well outside. So this system is not to play outside.
Okay, thank you very much. So let's move on to the next presenter. Yep, so here we have our next poster presenter for the ASMVR for the light triggers in virtual reality to induce ASMR. And we will have the poster presenter authors to quickly run down with the
poster descriptions.
Thank you. Autonomous sensory meridian ASMR is a tingling sensation that can help people reduce stress. And also ASMR can produce a feeling of relaxation and euphoria. So existing study categories 4 different kind of ASMR trigger: visual, sound, touch, and scenario. And light trigger is a sort of visual trigger. So at first, we analyzed some ASMR light trigger videos on YouTube that we want to have a primary impression on how the ASMR artists they help viewer to induce ASMR. So we found that there are 3 main points: the light interaction, ASMR sound, and emotion feeling. So based on our analysis, we applying them on our design. We created the ASM VR experience that we can not only help ASM artists feel free to select and control different visual light source by using the VR hand controller, but also we can let viewer experience immersive ASMR method that help the viewer to feel intimacy and help them to induce ASMR tinglings. Yes, that's all. Thank you.
Thank you very much. So a quick question to you. Have you considered any using physiological sensor such as measuring heartbeats or in the future?
I consider the haptics vibration in my future work, that because also the touch is another sort of ASMR trigger. So I want to combine them as a multi-mode interaction. Yeah, thank you.
Okay, thank you very much. So let's move on to the next posters. All right, so now we have our next poster for human copters wearable drone system for remote multi-directional teleoperations, and we have 2 other presenters today. So yep, let's invite them for the quick rundown for their poster.
Thank you. Hi, good afternoon, everyone. So our research is human copter. And in this research, we aim to provide a full directional cues to the user. And to achieve this, we propose human copter. So basically, we just attach the drone on the user with a shoulder mount and also with mounted on the helmet. And we also designed some 3D printed safety protectors to for the safety measurements. So, and to evaluate our prototype, so we designed a experiment. And in the experiments, we design a simulate environment with 35 points on the ground, and we will direct the user to walk around the points with 5 random points. And after the experiment, and we will give the user an interview. And in the interview, they feel like the force is actually clear enough, and they prefer to be not blindfolded because they feel like with blindfolded, they can feel the directional better. And if they are not blindfolded, they will try to defy the force when they see themselves walking to a border. Yeah, and thanks for listening.
Thank you for the really good rundown. So I have a quick questions for you. So have you ever considered in the future to use it in the implementations for maybe virtual reality or augmented reality, such as I would say that maybe some levitating effects or maybe some force feedback will be really important and really good to know for maybe future immersive technologies?
Yeah, that is actually our goal for the next step. So we will try to, first of all, we'll try to implement the whole system to a full body control. And after the full body control, we would like to implement it into maybe VR environments to be used in some simulated environments kind of thing. Yeah.
All right, thank you very much. Let's thank the authors again. So let's move on to the next poster.
All right, so we have our next poster for the effects of spatial and temporal deletions of a brand logo printed on a VR shopping bags. And we have the poster authors to quickly run down for the quick descriptions of the poster.
Hello, my name is Moi. In this research, we research for a shopping bag, and in this we research for recognition of logos for this for logos and is for display methods. And in this research, the most recognition rate was highest recognition display method was this 3D plus and footprint methods. And but in this research, used via sorry, VR used VR stores floor was nearest color and of this logo too. So and it was sorry, but the most recognition rate was the highest recognition rate was in the 3D plus footprint, but in logo 2, but logo 2 was the most lowest recognition, and we decided to we read off logo 2 and search for this one, these three logos, and the most that one the most highest one was finally the most highest one was this method. Sorry. The survey of this experiment is about research about logos to on the shopping bag, but we search for these three logos and three methods, and the most highest recognition was this 3D plus footprint method, and but the VR stores floors nearest color of this logos number 2, but so the most recognition of logo 2 was the lowest one, so it need to it need the logo color have to differs from the floors.
All right, that's all right. No problem. Thank you very much. So because of the time, so let's thank the authors again for the presentations, and we will quickly move down to the next one. Thank you. Thank you. All right, so we have our next poster, lyrics on to cityscape, and we have the authors to quickly present the work for us for a quick rundown and quick descriptions.
We propose a new music experience that allows people to carry the music video-like visual expressions matches to the cityscape. As a background of this research, high-performance mobile devices made it easy to carry music anywhere else. The listeners like so. Yeah, so this is an attempt that allows the listener to carry a visual presentation that is matches to the situation, depending on the listener's desire to listen to this music in that place. As a first step, we developed a mixed reality system that dynamically projects and displays animation of the lyrics of a song onto a cityscape.
Thank you for the quick rundown. So I have a quick questions for you. So I think that, so personally, I have used HoloLens before, and I found that it is actually a very powerful device to track for the AR cues and also use it for the augmented reality interactions. But one of the, I would say the limitations that I have seen personally when using the HoloLens is to use them on the outdoor. So how did you overcome the challenge, or how did you decide to allow the people to be able to, for example, see the cues exactly, even though the sun is really bright, or maybe only does it work on during a specific amount of the time or during the day?
Actually, I tested this system when cloudy environment and not bright environment. Yes, in this system is difficult to use in bright environment, but I want to so in the future I want to this system to for example AR device, I like mobile device AR. So so okay. Using video see-through AR device that issues, I think that issue is resolved.
So that's sort of like, for example, using the tablet to replace the HoloLens when the sunlight is really bright, and maybe we can switch back to the HoloLens when it gets to the comfortable level of the lightnings. Yep. So yep, that's very interesting, and can't wait for test the prototype actually by myself. So thank you very much again. So let's thank the authors again. So let's move on to our last poster for today. All right, so welcome back everyone. So now we are in the demonstration space for the ICAT-EGVE 2022. And now we will have our first demo presenter who is demonstrating their works for today. And yep, we will have him to quickly run down the project for us.
Hello, viewers. This is a demo of a VR programming in VR. So you can use these blocks to program in VR, have these 3D blocks. And this is intended for children to children's education of programming. And you can use these blocks and experience programming with moving these objects around in VR is inherently fun. So but current programming education tools mostly use the flat 2D screens. And so with the metaverse being more being promoted right now and booming, we expect to have these kind of tools to be used in programming education, and we want to utilize the VR experiences.
Thank you very much. So how does it look like? I would imagine that people will be able to quickly use that in the VR. And have you ever considered, for example, when they use the print, for example, in the display, can they actually see a cube spawn in the real world? Have you had any sort of the considerations for that in the future?
Yes, we are considering more visual effects to be spawned, but we are more considering that the experience of actually manipulating these blocks to be more fun instead of having the result of these programs being fun. So that promotes more fiddling around, and failing is actually more fun than actually you have. If you have to be successful in the program to have a fun result, that is not ideal. So you would want failures to be fun as well. So that is our concept.
All right, that definitely sounds very interesting for us. All right, yes, thank you for the authors again for the great presentations, for his demonstrations. So let's move on to the next demo presenter.
Thank you. Thank you.
Thank you. All right, so we have our next demo presenter today, and it seems like there is a really good and interesting setup in here. So maybe we could have the demo authors to present their work and quickly run down to what is going on in here.
Okay, this system is amplified coaster. You can experience roller coaster in here, okay? And by inclination stimuli and visual stimuli and moving forward, you can perceive ascending and descending, okay?
So it seems that the authors is going to do something to do with the gravitational. So let's have a look. How does it look like? So it seems that the authors are actually putting the participants into the wheelchairs, which is a kind of a really unique experience. But well, it seems that there is also another prop that's running on the ground to generate the initial force as well as the gravity force. Yep. So you said, how do you generate the gravity force for on the participants, or what sort of the scenarios you are trying to use in the setup?
Okay. One second.
Yep. So what sort of the immersive scenario they are using? Like, did they run in the grass field, or do they maybe play the car or something?
すみません、わかんないです。もっと、発展させていくってことですか。Okay. For example, in a park or parking area, you can experience amusement park attraction. Okay, so this system, the merit of this system is experiencing roller coaster in a limited space. Okay.
Oh, that's very good for the space management. All right, let's thank the authors again for his excellent demonstration. So let's move on to the next one. And thank you, Diane. All right, so we have our next demo for today, which is we have also have a title, which is the experiencing high-speed slash session in virtual reality environments, and we will have a demonstration author to quickly run down what he is doing and what's going on in the virtual environments.
I'm Trans Kiyamoto from Meiji University. Our research is experiencing high-speed slash action in virtual reality environment. Our system allows any players to experience high-speed slash action as seen in films or video games. The system, in the system, when the system detects the start of the action, the system starts the exaggeration of the motion of the player. The exaggeration is predict motion of the sword and show the motion blur in advance. For this exaggeration, players can experience the high speed slash action than the actual player's slash action. Thank you.
Thank you very much. Thank you very much. So it looks like Fruit Ninja to me, but in a virtual reality. So have you considered any different animations for the slashing animations at all? So for example, as you can see in here, where we have the authors trying to present the works by slashing it in the virtual reality space, and they are sort of like a very quick, high-speed slashing generation. So have you considered any different effects in the future? Maybe like a fire or maybe a wind sort of the things.
I think for fire, water, or wind, and so I think make from many animations or films or video games. Yeah, thank you.
All right, thank you very much. So let's thank the authors again for his great presentations. So let's move on to the next presenter for today. All right, thank you. All right, so now we have our next demonstrations today, which is the mingle with an amoeba. And it seems that we have a really interesting setup here for today, which is to use a really GUI interface to trigger the amoeba in the virtual environments. So it looks like the authors is trying to have someone to use the GUI Seki objects to present the sensations of playing a deformable virtual creature in the virtual environments. As you can see, the person is really enjoying the effects and also the sensations.
To scoop is very difficult.
Yeah.
So it seems like they are trying to communicate with each other in terms of how much content they should put out.
Yeah, I get, well, it feels cool. Yeah. All right, thank you.
Okay. Yep. So now let's have the authors to quickly run down to about his works and also to see what is actually going on in the backend.
Oh, this work's main goal is making non-living thing like a real creature by using combination of visual effects and strange haptics of slime. Yeah. The system is there. We use hand tracking. To interact with the amoeba and the visual effects is called shield haptics. This presents this gives the users shield vibration feedback only by using visual effects. Should I explain more?
No, that's all right. So thank you very much. So do you plan to create like a RPG game with a slime where people try to touch them? Anything like for the future?
Sorry, please say more again. Let's see. I haven't thought a lot about this, but to use this work, let's see. Strange haptics feedback can make なんでしょう。ちょっと待ってくださいね。
So maybe they can try to detect the enemy more better, maybe?
それもう一回お願いします。はい。
じゃあ大丈夫です。
大丈夫です。
All right, so because of the time, so we might have to quickly run on to the next demonstration. So let's thank the authors and his amazing work again. So thank you very much. Okay, so we have our next demo, and the author seems to be doing his work in here, and there is going to be the boom machine evaluations of VR game experience with switching the presence of haptic feedback. So maybe we can have the author to quickly run down about what's going on in here and what is he trying to do.
Okay, so this demonstration shows the research of VR game with switching the presence of haptic feedback during play. By placing a physical mobile robot at the same position as a visible object in the VR space, the user can get a haptic sensations when he make contact with a target. On the other hand, by placing a physical object at the out of that position, the player get strike and don't get any haptic sensations. And we investigate how temporal patterns of the objects with haptics and objects without haptics change impressions on VR game experiences. Okay, so let me show how this system works.
Yep, so let's have a look at how it looks on into the backend. So is this thing heavy or is it really lightweight? So how many grams is it? Maybe 100 gram or 50 gram for the headset? I mean, for the equipment, for the device?
Equipment? This toy hammer?
Yes.
Or, I don't know the detail. You help?
It looks like maybe 100. So yeah, that seems like a very lightweight equipment.
Not heavy, not too heavy. Yeah.
That's interesting to know.
Yeah, let's start. Real entity and real entity. And I get strikeout now. Half tick. And half tick. No half tick.
Oh, I really like the sound effect, especially when you try to smash it. It looks very stress relaxing to me. Well, all right. Thank you very much for your works, and that's really interesting to know your work today, and also keep going on with your good work. All right, so let's thank the authors for his great demonstrations again. Thank you very much. So let's move on to the next demo presenter. All right, so it seems that we have our next demo presentations for today, which is a demo based on moving interactions by controlling yourself in the virtual space. So that seems like they are trying to do something about how can they create the interactions by controlling their own self. So maybe we can get a closer look for really good details about what is the demo trying to do. So it seems that the user have to hold on to the objects in order to be able to control himself to walk around in the virtual environments. So maybe we can have the we can have the authors to quickly run down to what he is trying to do here.
We propose a method of movement in virtual space. The user becomes a In this demonstration, we propose a method of movement in virtual space. The user becomes a ball that can roll through the virtual space and is operated from first person perspective. There are several objects in virtual space which correspond to neutral objects in real space that match their appearance and movement. Yes.
All right, thank you very much. So how did the user can actually control themselves? Do they use the objects in their hands or do they have to use the controller to move their character?
The player use a controller to movement.
It's okay. Yeah, it's fine.
And what about the things that they are trying to hold on their hands?
Thank you.
Yeah. Players used to move to use club or stare, or hand.
So let's have a quicker look into it. So it seems that there are multiple small objects here. So is that means when they try to hold the objects, is that going to be represented into multiple different virtual objects, allow them to maybe put into some places, or do they just will be able to interact by holding it? No problem. So I think that we have going to be running out of time. So let's thank the demo presenters again. So let's move on to our last demonstrations for today. All right, so here we are for the last demonstrations for today, and probably we could have the authors to quickly run down maybe 30 seconds to tell us about what it is doing and what they are trying to do in here.
Yes. Okay, so we have worked with the rendering. Should I take it? We have worked with the rendering. Is this fine? Okay, with rendering glinty granular materials in VR. So granular materials are, for example, sand or any material that consists of a lot of small granules. And that could be very challenging to render because it looks so different depending if you're looking at it closely or far away. And also when it's a glinty granular material, which means that individual granules are shiny, then that's also very difficult to render in real time. So yes. Maybe I can just show like what it looks like. So our sand looks very different depending whether you look far away or I don't know if the or if you look very closely. It's like more detailed and it has glints that disappear at a distance. Yeah, and the way we have done it is using textures at close distances, which are procedurally generated, which, yeah, we have a way for doing that. So you can choose what the texture should look like. What else? Yeah, so we've solved the problems of having like very detailed textures up close, like what you would expect for sand, but very uniform appearance far away, and it's running real time, and the glints are stable. They're not like flickering everywhere. So yeah, this is something that's nice for VR because you can expect things very closely. Maybe otherwise you wouldn't care if you only had to see it from far away.
Thank you very much. That looks very interesting and challenging because how can you decide to optimize, especially with the performance in the virtual reality when they are trying to use and try to render all of the different amazing 3D objects. And I would really imagine that this can be really useful to create much more immersive and realistic environments for the user to experience and have a better embodiments and also the performance for running through specific scenarios. All right, so thank you very much. So here we conclude all of the poster and the demo for today. And I hope you enjoyed that. And make sure that if you have any questions, feel free to post it onto the Zoom and also the Slack, likewise also the Discord, and let us know, and we can pop the questions to each of the authors for you. All right, thank you very much, and I hope you enjoy the rest of the ICAT-EGVE 2022.
Hello, everyone. I would like to start
the fifth keynote talk session in ICAT-EGVE 2022. And the keynote speaker of this session is Professor Kota Minamizawa from Keo Media Design. And Minamizawa Sensei is currently the project manager of a JST Moonshot project, one of huge research budget in Japan. And his specialty is tele distance and haptics. So yeah, we expect very exciting talk about that field. 南澤先生、どうぞよろしくお願いいたします。
Hi, yeah, thank you very much for introduction. So, and thank you for inviting me to this keynote talk. So it's really appreciated because ICAT is a conference that I was participated every year when I was a graduate student. Yeah, it's really happy to introduce our researchers here. So yeah, I'm Kota Minamizawa from Keio University, Graduate School of Media Design. So I'm now, yeah, as I introduced, so I'm also the project manager at the at the JST Moonshot R&D program. So today, I'd like to introduce a bit about my kind of laboratory research, which is called Embodied Media Project, and many talk about the Moonshot Semantic Being project. So, yep. So my research, our research is about how we can empower and enchant and also create an empathy with having this kind of a digitalized kind of a human experiences, and how we can create the feeling or experiences that occurred on our bodies, because we feel the experiences through our bodies. So then it is quite important, we believe, that this technology can be embedded onto our body, then we can expand our kind of capabilities. So our project includes one is haptics, which is a sense of touch, as you know. So we are developing the kind of the haptic sensors and the haptic sharing tools that kind of transfer the haptic sensation from the distant places. So the tactile toolkit enables you to design any kind of the haptic sensations in a very easy way. Even the children can kind of design their own haptic experiences by themselves. And also we are also exploring how the full body haptics can expand our feeling of the XR environment. So the Synesthesia Wear project is, this is a wearable haptic display that providing haptic sensations on the entire part of your body. Then it is also connected with the cyber environment so that you can receive the perception from the cyber world when you are walking around the public spaces. And also that we are trying to also explore some kind of a physical and tangible things like a special animacy project. This is a molecular architecture project that is not on the body, but more like on the environment. So how the environment can react with our interactions. So then this dynamic world is connected with the cyber world, and it reflects the information from the cyber world to the physical world. And also we are also exploring how we can augment the human body itself. So then this kind of a fusion project is trying to amplify your arms. So we are attaching the third arms and the fourth arms on your body. And these arms are connected sometimes by yourself, but sometimes the other people in the remote place can also control this kind of the alternative bodies that you can collaborate together. This is kind of a wearable kind of a tele-distance avatars. So then tele-distance avatars, so I will explain a bit details later, but we are not just developing the technology, but also trying to install that or deploy that into the society. And also recently, actually, we are also exploring the new potential of the sensing the human emotions, like using physiological sensors. So we are kind of capturing the human emotional signals, then trying to deliver that kind of the human internal emotion over the distances, or sharing that kind of emotional experiences together. So this is kind of a collaborative project with the performers or artists or musicians. This kind of the daily kind of emotional feelings can also be delivered over the metaverse or virtual reality world. So that is the kind of the entire picture of our project. Then one example what we are doing in embodied media project is this is the synesthesia suit project, which we did in 2015. So in this project, we are collaborating with the game industry and trying to create new type of the full body immersive virtual reality experiences using full body haptic suits. So because as you see, this is the collaborative project also with Sony when they are delivering the PlayStation VR headset. So then before they launch the product, so we start to consider how we can promote this kind of new tools or new experiences of the game users, and how we can provide the concept of the future games like 20 years later. And then we come up with the idea of this kind of a full body haptic suit. So let me see the video. So yeah, in this research, as you saw in the video, so the user is wearing the suits and play the game with the VR 360 degrees of VR. Then when they kind of shoot the enemies or hit by the enemies, so they can feel the haptic sensation on their bodies, and also they can feel the full body kind of the vibrations when when you warp from some place to place, or when you are jumping or something, like when you are kind of squeezed by the space. So you can feel various kind of the actually haptic sensation on your body, and it helps you to fully dive into the cyber world. And also that we got a lot of kind of the feedback from the users that they forgot about their physical bodies. They forgot about their standing in the event place, and they fully dive into the virtual world. Yeah, that is our embodied media project. But I'd like to more kind of deeply dive into the teleexistence part, because I'm not sure how many of you are recognized, but the ICAT-T is about the teleexistence. So then ICAT is actually founded by Professor Tachi, who is my doctoral supervisor. And also when he come up with the idea of teleexistence in 1980s, so he also kind of built this ICAT conference to spread the concept and also go dive into the research. So then in collaborating with the Professor Tachi, I was also in charge of developing the teleexistence system called Teresa 5. So this is the system that can deliver not just the visual and the auditory sensations, but also the haptic sensations on your 5 fingers. So in this system, as you see, the robot is synchronized with your motion, and you can see what the robot sees and what the robot hears. And also, you can also feel the sense of touch from the robotic fingers. And this robotic sensor, the haptic sensors on the robot fingers, consists of the vibration sensor and also the force sensor and the thermal sensors. So these 3 kind of elements of haptics are combined together to deliver very kind of a high realistic haptic sensation. So you can feel as if this kind of bumping of the blocks. And also you can also feel, for example, when somebody grasp your finger, so you can feel also the warm sensation from the hand or even cold sensation from the ice. So, and also you can of course feel the more like textures. So when you, for example, drop the marbles to the cup, so you can feel this kind of a tiny haptic sensation on your skin. So that is what we developed as a teleexistence platform in 2012. So then using that kind of the technologies, we are trying to explore several potential of the use cases in the real applications. So in this project with the construction company, we installed the teleexistence robot in this kind of construction vehicles. So because we had a big earthquake, so then 10 years before, then we need this kind of a surveillance kind of a systems to observe and fix the environment from remote places. So, and also in another kind of example is that in this project, this is an actual welding ceremony held in October 2015. So then in this case, the grandmother was hospitalized. She cannot participate the wedding ceremony in Tokyo. Then we actually collaborate with them to provide the avatars. It is, as you see, it's a kind of a customized paper robot. Then the grandmother can connect to the robot. Then she can. It's the first time for her to meet with their new granddaughter. So this is saying that, so that this is the grandson of the grandmother. Then as you see that, so if we can also do similar kind of things with the remote online communication like Zoom, but without having the bodies, the people can easily forget about you. But with having the physical body, we found that it is possible to be there, and also the people surrounding in the environment can also believe that she's coming here. So then she said that she could participate. She could actually participate the wedding ceremony, and also family can also really appreciate about that. So like that kind of use cases we explored. So we also have a chance to discuss with the XPRIZE Foundation, which is a United States foundation funded by several kind of entrepreneurs like founder of Amazon or Google or something like that. Then they are exploring the kind of challenges that creating a new society and new businesses. Then with ANA, which is an airplane company in Japan, so we come up with the idea of this kind of a global challenge called ANA XPRIZE, Avatar XPRIZE. So which is a global challenge that facilitates and motivates the people in the world to create the robotic avatars and also to apply the technology into the new business and the new society. So then we actually presented the TESA5 system in Visionary Summit, which is a kind of a competition to select the theme of the challenges. Then NA won the challenge, and also then Avatar XPRIZE was launched in 2018. So like that, so starting from the Professor Tachi's invention of the teleexistence, so the technology is getting advanced, and also the social kind of the atmosphere or social demand also increased in around 2016. Then thanks to XPRIZE and also the other kind of also the metaverse or virtual reality evolutions, so then there is now a lot of kind of the industries and the startups starting to develop the robotic avatars and creating new businesses. So but also as you know, we had COVID after that. But many kind of the startup companies also starting to explore new challenges during COVID to connect the people over the distances because we couldn't meet together. But with having avatars, we can provide the solution for the people to meet together over the distances. Then we also established a new startup company called Teledistance Inc., which is chaired by Professor Tachi, and I'm also the technical advisor of that company. So let me see the video from the Teledistance Inc. Yeah, the mission of this company is to go beyond the distance. So it's this company trying to create a new work style or lifestyle that people can work from over the border of the countries. So now we are actually installing this kind of the robot into the several kind of the convenience store in Japan, and also exploring how we can get the workforce not just from the human body, but also from the distant places as well. Then also the XPRIZE actually was conducted the final testing this month. Actually, this morning I actually met with the director of the XPRIZE. He's now just visiting Japan. So then I also visited the XPRIZE final testing and also observe what was happening there. I'd like to introduce a bit about that. So in the XPRIZE, Avatar XPRIZE final testing, so they created the environment like looks like Mars, like that. So then there is an environment with several kind of the tasks installed. The first task is the communication. It's like a oral communication with the real human. So human, the robotic avatar need to discuss something. Then after that, it's a simple task with the pushing button to open the door. It's really simple, but still you need an arm. Then third task is a bit difficult. It's a pick and place. You need to pick up a bottle. Actually, there's several weight of the bottles, and you need to select the heavier one. Then with feeling the kinesthetic sensation, weight sensation from the cockpit, that you will pick up the heavier bottle and place that. So then the fourth task was drilling. It's a real drill, electric drill. It's a bit heavy, like 2 or 3 kilograms. Then you need to hold that, then push the button to turn the drill. Then you need to remove the screw to open the door. So it's a most kind of the difficult task that many actually team couldn't pass that. Actually, only 30% of the team could pass that. So then you need to, because you need to pick up grasp a bit heavy machine, heavy tool, then you need to also push the button with the index finger. Then also you need to kind of precisely locate the drill on the screw to remove it. So then after opening the door, so there's kind of the stones behind the curtain, black curtain. Actually, you cannot see the stones. Then you need to insert your robotic hand from the avatars, and you need to touch the stones. Actually, there are several textures some is smooth, some is rough. Then you need to pick up the rough texture stone. So this is kind of a haptic task, texture task. So then you need to pass all the tasks. The team need to pass all the tasks. Actually, initially in this Avatar X Prize, 99 teams registered in the beginning in 2018 when we announced the event. Then there's several kind of selections happen. Then finally, in the final testing, there's 17 teams participated. Then I think only 5 or 6 teams could successfully reach the goal with clearing all the tasks. Then first prize was Team Nimbro, which is the Bonn University in Germany. So it is really, really nice kind of robotic avatar system actually, with having 2 arms with the human-like hand, and also the head is interesting. They have stereoscopic camera and tablet, but not just that. It is manipulated by 6 DOF arms. So actually they have 7 DOF arms, 6 DOF maybe. 3 robot arms are installed in the robot. The head itself is also manipulated. It means that you can move the head very freely. In some tasks, maybe you can see there. So then on the display, they created the facial image without wearing the HMD. So they took the picture of the operator just before they start operating. Then they control the mouse and eyes. Yeah, as you know, with kind of like using the fake face technologies, so they can capture the motion of the eyes and the motion of the mouse. Then they reflected that on the facial image of that operator. Then, yeah, we can actually feel that there is the person there. Other teams using just the image of the head with HMD or just animation, but only this team can actually provide the actual facial image. And also the second prize was the team Poland Robotics in France. So this team is actually a startup company. So they started from the university and now they are trying to sell the avatars in the American industry. So it's also really nice that this kind of the competition can also push this kind of the new businesses forward. But anyway, so like that, so now the robotic avatars are kind of starting to kind of spread in the society. In Japan, there's also many startup companies are starting to do their own businesses. Then on the research side, so the Japanese government also starting to consider that this kind of the new use case of the robotic avatars or metaverse or virtual reality is necessary to create a future society. So then in the Moonshot project, so then set the goal one with the mission, which is called Goal 1, which is realization of a society in which human being can be free from limitation body, brain, space, and time by 2050. And this is the kind of more like a very big milestone of the government strategic mission of this Moonshot. Then the actual topic of this project is something like what we are doing now. So go anywhere with the avatars or play a lot of kind of the 3D games or 3D entertainment from the metaverse, or augmenting our body or also cognition or perception with the wearable technologies. So this kind of a component will be combined together to create a new society in the future. On the other hand, so that we also started to think about that not just speed up our experiences, but also this kind of the robotic avatar and also the teledistance technologies can be kind of expand the diversity and inclusion of the current society. It means that, so for example, I'm wearing eyeglasses, so then I don't need to kind of worry about my bad eyesight. I cannot see your faces without glasses, but I don't need to care about that. So then, like that, if we have cybernetic avatars as our alternative bodies, and what if we can overcome various obstacles that we have and that hinder our well-being? Like COVID is one of that. The pandemic makes us impossible to physically communicate together or go outside. And also of course, the age is also a problem that now the Japan is a super aging society and many people have a difficulty to go somewhere or meet friends or do work. And also the physical disabilities or perception disabilities also are very kind of an important factor of the current society. We need to make society more inclusive. So like SDGs also suggest that, so that we need the new way of promote the empowerment of the people. And also that we need new way of working freely from any limitations. And also we need a new type of education and skill transfer that empower the people. So then we believe that so the cybernetic avatars or this kind of the robotic avatars or even the virtual avatars as well, it's a solution for that. So yeah, our mission in this moonshot project is lift the barrier with robotic avatars as alternative bodies. So then our project is now called Cybernetic Being Project, which is something like a beyond human being. Then we are trying to create a technology and also social system to sharing the experiences and also transfer our skills. Our vision for the 2050 society is that the creating a future society where diverse people have cybernetic avatars as your alternative body, and we can share our skills and experiences together to freely engage in social activities, regardless of our disabilities or any limitation of our bodies. So then in this project, we are mainly targeting two directions. One is how we can enable the people who have difficulties to behave freely in the society with avatars. And the second one is that how we can share our experiences and improve our skills through the avatars, how we can create some kind of a collective knowledge with this kind of embodied informations, or how we can expand our capabilities of our bodies. So the going toward these two kind of the directions. So we established the team with 15 researchers. So this is kind of the younger team, the relatively young team, considering this kind of big project. So then mainly around 30s or 40s, the researchers and also the startup companies are collaborating together to create that kind of the technology and the society. So there's a team that's focusing on how we can augment our cognition with the avatars, because if we have different bodies, we have different mind, and we can expand or we can change our body cognition. And also the second team, parallel agency, is exploring how we can copy our experiences. So it means that with using the digital world, so we can copy and paste our behavior and also the sensory informations. So then it means that we can exist in multiple places at the same time. Even it's a real world or virtual world, we can exist in the several places at the same time. then we are trying to create a technology and also the understanding human brain, how we can adapt with multiple bodies at the same time. And third team is focusing on the collaborative skills. It means that if 2 or 3 people are controlling one avatar at the same time, we can combine their experiences and skills to create kind of a super avatar, which have different skills of different people at the same time. The fourth team is like a connecting everything together over the network. So we need the infrastructure that enables these kind of the new features on the one platform. And 5 teams, it's also quite important because we are also collaborating with the actual users, like disabled people or senior persons. So we are have a community with this kind of the people, like potential users. Then we are actually delivering the technology to the user to explore how they use this kind of a new way of social behavior and what kind of potential they have. Then 6th team, this is also quite important. This is a team of the social design, which is thinking about how we can create new legal rules, because we don't have avatars in the current society. Then in the current, I think not only in Japan, but in global world, so the current social policy doesn't allow the people to exist multiple places at the same time, for example. When you come to Japan, you need to pass the immigrations. But with having very realistic avatar, actually you can pass that over the network. But what if that avatar earn money, for example, or that avatar do some crime? What kind of the legal rules, what kind of law can cover that? So then we are trying to design new social rules that covers this kind of a cybernetic being society in the future. And also that we also have the person, Emma-san, who is STS, Science and Technology for Society, researches that how we can adapt, how the people or society can accept this kind of a new concept in the future. So then, yeah, again, that we are exploring the new potential of the avatars, that how we can change the mind or how we can copy our experiences and how we can merge the human skills together. Then let me show several examples of our recent researches. So then in the first team, cognitive augmentation, we are exploring changing human body and understanding how our mind or how our cognition or will be changed. For example, like if we have really kind of a muscled avatar or maybe narrow avatars, your actually perception of the weight is changing because you can believe that you are stronger if you have muscle body. Or if you have a flying body like birds or dragons, you are not necessarily too afraid to fly the sky. I think you have experience in VR that if you are standing on the very kind of the edge of the mountain, so if you see the kind of a town or environment very kind of the bottom, so you feel really afraid. But if you became a bird avatar which is flying, so this kind of the afraid will be reduced. And also if you have this kind of a doctor avatar and the normal avatar, so actually the several cognitive task performance will be changed. If you have the molecular looks like smart avatars, your actual performance will be also improved. So this kind of the change of the body is changing the mind is one of the current findings we are doing. And also we are also trying to change your cognition through this kind of the AR technologies. In the Dementia Eyes project, so we are creating the filter that changing your visual perception into the one of the dementia patient. So the dementia patient have several kind of diseases, symptoms, and also they cannot, for example, see the black floor. If there's a black carpet like here, so it looks like a hole, and they tend to afraid to go walking, start walking on the black floor. Like that kind of experience can be provided from this kind of AR filters, and also that you can understand how your perspective will be changed when you get dementia. And also that we are working with several kind of doctors and nurses, and after these experiences, they are starting to change their communication or interaction with the patient. And also in the parallel agency team, so we are trying to explore how we can make it possible to duplicate our bodies. So in the parallel people project we did last year, so that there's, as you see, there's 2 robotic arms, which is controlled by 1 person. Then we are trying to copy your motion in both the side A and side B. Then you can actually play the ping pong for both with two people. Actually, in the distant place is also fine. And also in the collaborative ability project, so we are trying to make a platform that combining 2 persons' behavior on 1 avatar. So in this case, so that they are controlling the robotic arm, which is avatar, to pass the task. So then, yeah, we found a very kind of a good benefit that you can share the cognitive load of the task if it's too difficult for you. So maybe some part of the task can be shared by another person. Then, yeah, we can actually combine both users, both operators' performance. Then we can improve the performance of this robotic avatar. Yeah, actually 1 + 1 gonna be more than 2. Then, yeah, we are also trying to explore several potential with this kind of the skill sharing with the avatars. So in this case, this is an example of what we did with the Ministry of Agriculture in Japan. So actually, the person left side is an actual farmer, and they are now farming rice. Then right person is a beginner. He don't understand how to do it. But with sharing the bodies, the beginner can actually feel how the professional person moves their bodies and how they feel, because we also have the haptic sensations. So then we can also share the haptic sensations for the both side. Then we are starting to understand that this kind of a platform can be also used for the skill transfer as well. Maybe I can skip. So then we are also starting to share not just this kind of physical experiences, but also the emotional experiences. So recently we are creating the physiological sensors that can capture. This is a wearable sensor on your wristband that can capture your heartbeat, heart rate, EEG, and also the skin conductance. Then we measure how you are feeling, like you are relaxed, or you are more like afraid, or you are concentrated on something. Then in the actual performance of the music live, we capture the 50 people's kind of emotional changes. Then we are trying to deliver that over the VR. We record this kind of a 360 video and sound. Then not just the visual and the sound, we are also trying to deliver the emotional feeling as well. And finally, we'd like to introduce several of our trials that we are doing in Avatar Robot Cafe. So this is the this Avatar Robot Cafe is operated by Orilab, which is a startup company in Japan, and we are collaborating with them to create a sandbox to apply semantic avatar technology in the real users. So then in the cafe, actually, there are various disabled people are working remotely, and they are controlling the avatars and also the communicating with the guest of this cafe. So let me show the movie that we have done in June this year. So in this case, we are applying our parallel avatar experiences in the cafe. So it means that the one disabled robotic operator, one disabled operator can control 4 avatars, 4 robotic avatars at the same time. So they are disabled in their home, but they are now have 4 bodies. So he's Masa, one of the pilot. As you see, he's have a very kind of a heavy disease, and he cannot move their bodies. So actually, usually he's controlling manipulating his computer with eye tracking because he can move his eyes. Then now he's in the avatar Orihime and saying welcome, say hello to the guest. And he's inviting the guest to the table. Or let's go there. Please go to this table. Then on the table, he's there. So he's already here. Then now he's starting to say, oh, say hello again. Then what kind of coffee, what kind of juice you'd like to have. Then during communicating with the guest, another body is coming with the coffee. So now this is also him. This is also Masa. Then now you can see 2 Masa at the same time. Then yeah, they have, during their communicating with the guest, he can also bring the coffee using another button. Then actually this is the kind of a new experiences of the body. Then also we got a lot of feedback from the operators, pilots, and also the customers that it is really nice that they can do from the beginning to the end. Because if you can use only one avatar, you can do only one task. But now you can go anywhere. You can jump several avatars in the cafe, and you can go. Actually, you can feel as if you are walking. You are go around the cafe, and also from saying hello in the entrance to the end, he can serve the customers. So it can provide very kind of a feeling of success to the operators. And also for the customers, it is also nice because it looks like a very kind of a nice hotel or a nice restaurant because one staff can welcome you and serve the drinks and say goodbye. So looks like a very high quality hotel or restaurant, like with having really high hospitality. Yeah, that is the experiment, one of the experiment we are doing actually in the cafe. So usually if you would like to visit this cafe, you can go there. So it is placed in the Nihonbashi, which is really center of Tokyo. Usually it is not parallel mode. Usually one pilot is using one avatar, but you can still communicate with the avatars, and you can also have really nice coffee and also lunch. So yeah, actually also I'd like to introduce our latest experiment we have done this month. So this is the installing the collaborative avatar skill collaboration in the disabled cafe. So in this case, we actually installed a robotic arm in the cafe, and we tried to create pancake. So now there are 2 disabled pilot, but they are controlling the robot arm together to decorate the pancake. Let me see. So we selected the pancake because it is kind of flexible and it has a kind of a sense of creativity because it is not the fixed task. You can decorate anyways. Then we think that it can kind of facilitate some kind of creativity of the pilot. So then like that, so he's one of the Cardi is one of the pilot. He usually use the wheelchairs and also his kind of the muscle power is really weak. So then in this case, he collaborated with Masa, who was the previous pilot using eye tracking. So one pilot using eye tracking, another pilot using mouse trackball. Then they are watching each other's mouse cursor and also the exchanging their ideas to how to operate the robot arm and how to decorate the cake. Yeah, we believe that with having this kind of avatars, not just expanding human abilities, but also we can expand our creativities. The different characteristics can combine together to create new characteristics, new personalities. So it is, we think, the new type of the concept of self. So the concept of self is now not just about our physical body and the physical mind, but it's gonna be about a new body, alternative body, and a new type of the definition of the human being can be created. Yep. So yeah, we are like that. So we are trying to create a future society like diverse people can use the cybernetic avatars and also expand their experiences and also the abilities. So then we believe that this can enhance, expand our social diversity and also the inclusion, and also each single people can have more kind of the more diverse life experiences. And also, it is also quite important to not just think about the technology, but also thinking about the lifestyles and also the social society itself. So we are now launching the Cybernetic Avatar Society workshop, which is a collaboration with lawyers and also the industry persons and also the governors to discuss what kind of the issues or what kind of the potential troubles can be occurred with this kind of the new ideas, and how we can design the rules or legal kind of a new laws according to that. So we are discussing about how we can create an intellectual property for the shared skills, or how we can think about the immigration with the cybernetic avatars, or how if the multiple bodies doing some kind of making some troubles, how we can think about the legal responsibilities, and how we can accept the people working with the avatars. Yep, this is the last one. So we are actually, I think that we are now have a vision that the technology, this kind of the avatar technology, can not just quantitatively augment our human being, like having more power or more speed. That is more like a quantitative augmentation, but we can also think about qualitative augmentation, like having a better quality of life, or having a better behavior, or having better social connections. And I think we can also expand the concept of self. Now the identify of the self is also changing. how we can think about that. And then we'd like to try to expand our quality and diversity of the experiences that one person can gain in a lifetime. Okay, it's time. So thank you very much. So this is, if you are interested in, please also watch our website. Thank you very much.
Namida Sensei, thank you so much for your great talk. We'd like to have a discussion time. So yeah, if you have any question or comment, please raise your hand. Also, you can write your question on Discord, and also it is possible to raise your hand on Zoom to start your question as well.
I really like a lot of the different ideas here. They're very cool. I don't know if you've thought about this yet, but I wrote down that the goal of Moonshot is to allow humans to be free of body, mind, space, and time. I was just curious, have you thought any way about how we could be free of time? Are there any ideas on that yet?
That's actually always we are also discussing, because this kind of a project is really busy. So then we are always most struggling with the time. So we are trying to be free from the space and the body, but actually that is the lack of our kind of technology. We don't have any solution on how we can overcome that time. Yeah, that's true. Actually, we don't have our idea yet. But actually, some researches we are doing actually is to compress the experiences. So because with understanding human emotional changes or behaviors, so we can kind of compress the time of the experiences. Because I think if you remember something, or if you think about your childhood, it was maybe 5 years or 10 years experience, but you can remember that, we can imagine that just in few seconds or few minutes. So I think it is about how we remember or how we can keep the experience in our body. Then we think that this kind of physiological data, it means that our emotion will kind of create some kind of a selection of our experience. Then, it is just upcoming researches. We are still just starting, but we are trying to compress this kind of the experience time into maybe 10% or something like that.
Thank you. Any other question, comment?
Or online, maybe? Sure.
Yeah.
Thank you so much. One of my questions is around tele-existing as a non-human. So sometimes we want to experience being a dog or being a mythical creature or something. So can you talk a little bit about non-human experience augmentation?
Yeah, so actually we are not so much kind of doing a lot multiple kind of the trials for non-humans, but actually we think that it has a really big potential, because we can change our bodies in the various kind of the species, or even non-animals, or even becoming trees, or even becoming some kind of a robot with many arms, for example. So then we don't have solution yet, actually, but we are now starting to explore how we can create new type of sense of agency to the different type of the bodies, and how we can, because also this kind of the avatars should have some of the autonomies, because if you need to control entire part of the body, it's really annoying. So we need autonomy for the avatars. So how we can kind of the intent, our intent can be delivered. If it's a human body, I think it's easier. We can understand our body schema. We can expect how it works. But if this avatar has a quite different body that we cannot imagine, or we cannot understand how it works, how we can still deliver our intent. So yeah, that kind of things might be a new type of the fundamental researches to explore how we can become non-human being.
Thank you very much.
Thank you for interesting talk. And so my maybe the comments or the question is really closely related to the previous question about the idea how to overcome the time restriction. So I don't know this, it's really hard problem, and then the time constraint could be defined in multiple way, but the one example is speed of our motion, for example. I think that speed of our motion is really hardly restricted by physical property of our body. So and the previous neuroscience evidence actually already showed that our neural activity can be quickly rehearse what we want to do. For example, in sleep period, so the neural activity can be replayed more quickly than we are waking, and then so we can also imagine the sequence of the motion of the action more quickly than our physical speed. So then of course there is a really serious problem about how to read out that kind of signal.
Yeah, you are expecting.
No, I'm not yet. So but if it's possible, maybe we can overcome the limitation of the body speeds, and more we can probably improve the throughput from the what we want to do to the mechanical action. What do you think about that?
Yeah, as you know, we don't have solution.
Yeah,
it's kind of the open question, but recently we are also thinking about because as you say, the body has a limit of speed, but now actually if we can connect our brain or our nerve directly to the robot body, avatar body can be faster than our physical body. So then we are trying to start exploring how we have the faster body than human body, how our brain can be adapted there, and how this kind of the new body schema can be reflected maybe in the future to our physical body. It's not kind of the not overcome the time, but it's kind of the speeding up our kind of the sensory motor kind of schema or sensory motor interaction. That was one thing, maybe one thing we are now starting to think about. But yeah, actually, it's really great. You can also discuss further about that kind of things. Yeah.
Thank you very much for very interesting discussion. And I thought, yeah.
Yeah, very good talk. And I just wonder, did you ever think about maybe expanding the range of like what we sense, like looking at things in infrared in addition to to the visual spectrum, and then just mapping that in so that we get a different awareness and even ranging. To get a better spatial awareness.
Yes. So this is we called that kind of the idea about augmented teleresistance before. Like we actually have tried that infrared eyes with the teleresistance, because as you say, so we can have any type of the sensor on the robotic body and we can transfer that into our kind of the perception. So then For example, another example might be we can also, for example, changing body motion, body kind of the speed of the body to the double on the, for example, robotic avatar. It means that your motion, the angle of your motion is double in the robotic avatar. Then when you look right, it looks opposite side. That you can be some kind of all, but it also works. So the changing or editing or enhancing human perception is also really nice topic in when we think about the new way of using intelligent design technologies.
Yep. Thanks. ありがとうございます。Thank you very much. Is there any other question? Yeah. Okay, then, yeah, Minamida Sensei, thank you so much for
Thank you very much.
Presenting quite interesting trials, and we hope we can have actual cybernetic being soon. So yeah, we are very much excited about that. Thank you.
ありがとうございました。
Thank you so much for your participation to this ICAT. And this is not a closing session. We have actual closing session tomorrow, but now is a good timing to announce about the next ICAT. So Michael, could you start your introduction? Yes.
There's a video on as well. There was a video again.
Sorry, I didn't.
Yeah, but you hope for the best. Okay, hi. My name is Michael Mansker, and I'm from Dublin, Trinity College. And okay, it's a great event now, but we have to think about what we do next year. So my colleague John Digliana and I intending to host the conference the next year in Dublin. Yeah, the dates are given here as well. Oh. Yeah, just to say that we have the history of having a few conferences run from our lab. So we are the Vision and Graphics Lab. Yeah, this is just a number of conferences that we have hosted over the last time. So this is actually area view of Trinity College. So we have been around for some time. We've been trading for around about 450 years. So Elizabeth I founded the university in 1592. It was. So then we are part of the School of Computer Science Statistics, and within the school we have a number of themes, and one of them is graphics and vision. So we do a few things. We are 9 academics. I don't know, probably a lot of you know Rachel McDonald, Carol O'Sullivan, part of the group. As I said, 9 academics, 7 researchers, almost 30 PhD students. We have a lot of taught master students, so 140 of those. We cover a lot of perception work, particularly that's Rachel and Carol, and a lot of postdocs. Yeah, from graphics hardware rendering, vision, and signal processing as well. So there's also computer engineering group. They do a lot of work in computer engineering and vision as well. Okay, so to teach obviously as well. So we have the master PhD program, and then also interactive digital media. So that's just the university. Few highlights. So one of the leading university, I guess, in Ireland, and in the overall scheme of things, it's not bad either. And Ireland has become kind of the base in Europe for a lot of US companies. As you can see here, this is the Docklands. University is over here. And you can see there's quite a few companies that have heavily invested in Dublin. So it's basically the European headquarters like Google, Facebook, or Meta, you should call it now. Twitter, LinkedIn, you name it. There's a big Intel factory outside Dublin. It's actually the only one in Europe that has been around there for 30 years. So it's a big hub for software as well as hardware. Bit about Trinity College. That's the nice bits. That's the old library. You probably noticed that in Star Wars as well. It was modeled on those. Book of Kells. So then we are in a city center. That means we can organize social events in walking distance around the nice old campus. Does it progress automatically? So the only thing left then is I hope you join us next year in Dublin. And if you have questions, contact me. Thank you.
Thank you. Thank you very much. And this is a conclusion of today's oral session. And we are going to visit Gundam factory. And we need to take a bus from here to Yokohama Yamashita Futo. So please don't miss the bus. The bus will be depart soon. So yeah, please get out this venue with your stuff, and we can take it. And one thing, after Gundam Factory, we have a banquet at 7 p.m. at this location. And you can find the map in backside of your name tag. So after enjoying Gundam, please walk to the venue. It takes something like 13 to 14 minutes. So please check the location. And also, there is no bus from banquet venue. So please also check how to get back to your hotel by yourself. Thank you.